Hello, everyone, and welcome to the fourth and last session of the BICA 2025 conference. Let's get started with the schedule with the presentation that will be performed by Salvatore Di Stefano. Go ahead, please.
Okay, thank you and good morning, everyone. I'm sorry for not being in Mexico, in Puerto Vallarta, due to other business and deadlines, project and so on. I was not able to organize myself, and it's a pity because I know that Mexico, I went there some time ago. It's a really wonderful place, and especially in this period of the year. So I am not so happy to be remotely presenting this work. It is more or less, how to say, position paper on a that try to define a sort of taxonomy of neurocomputational architecture, jointly done with Max Talanov, that has this double position in University of Messina and in this AI Research and Development Lab in Serbia. This is the agenda. I will try to initially introduce computational and highlight the difference between computational and biological system, then switching from a system engineering perspective, I will define this neurocomputational system and introduce a sort of taxonomy with some final thoughts. Let's start with mainly the difference between a computational digital system and biological system. If you want, computational systems are usually discrete, structured, precise, and digital system, while neural systems are typical analog, working in continuous time, noisy, multimodal, and so on. The output of a computational system is usually discrete, deterministic, precise results, while in a neural system we have complex or even probabilistic output, prediction, regression, or something like this. Also used for even decision and so on. The problem-solving approach and how to say, the machine model is mostly a von Neumann machine model that it's based in computational system, digital von Neumann model with a memory, a CPU, and devices and I/O devices connected by a bus that needs an explicit program to work on. While, as you know, a neural system is mostly based on neurons, synapses, astrocytes, glia, and so on. It's non-von Neumann architecture that does not have usually a traditional concept of memory, but is mostly based on a learning algorithm, and it's mostly massively parallel. So in both cases, we have pros and cons. For example, usually neural systems are quite parallel but also redundant, so are quite much more resilient than digital system due to their plasticity and so on. The performance are quite fast, usually for discrete operation, for calculation in digital system, while are not so fast in neural system, unless, so maybe not so fast in terms of a single operation, in terms of how to say, speed, but overall, since they are massively parallel, overall the throughput is also quite fast. And another big, how to say, and really important advantage, pros of neural system is that it's quite efficient usually, especially in terms of energy resource more efficient than computational system. And what we can say in both cases, of course, computational systems are Turing complete, we know already, because it's a machine that was born from the Turing theory. It's an evolution if you want, while neural systems are Turing equivalent, accepting, of course, the bounds related to biological limits. We don't have an infinite tape that can implement a Turing machine. But we can say that with exactly this limitation, it is Turing equivalent. So can solve more or less the same problem in bounding the inputs, limiting the inputs to a given to the limitation of biological limits of the traditional system. So our goal was to try to merge and define a taxonomy between neuro-computational system based on a system engineering perspective. So in a system engineering perspective, define a system usually as a group of parts combined in a way that creates one or more emergent properties that focus on capabilities not possessed by the separate part. The key of a system is that the overall system, the whole, exhibits properties that are not shown by a single component, by a single part. In this work, what is a system, an ontological framework, there is a sort of ontology defined on system that is very briefly described this, but it's also the starting point of this work, where systems are categorized as real system and conceptual system. Real system, and then in different other ways, real system are those that really are really implemented as physical system, while a conceptual system can be even implemented or can stay as abstract ideas of system as a blueprint or something like this. Based on this difference, we elaborated, it's a starting point of elaborating our taxonomy. So we have real system and conceptual system split by this line in between. Just it's a simple von Neumann, is a simple Venn diagram, Venn diagram, where we identified neural system and computational system. Both neural system and computational system are both conceptual and real. But what we split them as conceptual system, conceptual computational system, and mostly software, while physical, real computational system are hardware one, we know already, and we have something similar on neural system. They are both, how to say, conceptual and hardware, real one. We are mostly interested in exploring the, of course, overlapping between these two sets. So what we defined as neurocomputational systems. So computational systems that exploit exactly the model, the powerful of neural system jointly. So, and these are, according to this description, split into software neurocomputational system and hardware neurocomputational system. So, usually software neurocomputational system are usually AI-based. So, AI neural models apply to software. So, usually, typically, machine learning, neural network, and similar that are populates this part. While hardware one are the novel, let me say, architecture, like, for example, spiking neural network circuit and devices like the Interlohi or IBM True North or North Pole or similar. There are a lot of them, or even, how to say, the hardware implementation of by memory stores of neural architecture. So we can say that these two classes, these two categories can be expressed this way. But these have been better characterized by this taxonomy. As you can see, we have a computational system, neural system, then from computational and neural system, we create this neurocomputational system and split into software neurocomputational system, as we said before, AI machine learning based model, neural network based model, or hardware neurocomputational system, what we said, for example, spiking neural network devices and similar. And in particular, we in a system, we combined these with the traditional system according to identifying these four taxonomy. So in terms of we can have both software and hardware that can be classical and neural. So if the hardware is classical, we say that we identify them as CH, classical hardware, or neural hardware, and software, it can be classical software and neural software. So it looks like as a Flynn taxonomy for who know the Flynn taxonomy. This way, we identified these four classes, these four categories of classical software on classical hardware. This is the traditional, and we are not much interested on it. Classical software or neural hardware, neural software on classical hardware, and neural software on neural hardware. So the idea is to combine these two models, classical and neural, all together, and see what are the four categories that was born. So based on it, we defined this taxonomy, and okay, the first one we know already is a traditional computing based on a von Neumann machine, classical software on classical hardware. And we know, as we said before, it's quite precise. We can implement a grid control, a symbolic manipulation, exact calculation, and so on. There are plenty of examples in this class, and I will not waste more time on this. Neural software and classical, even this should be somehow well known to the audience, so it's a quite AI neural network running on classical hardware. So for example, a neural software executed on conventional digital hardware such as CPU, but that can be also accelerated with the GPU, NPU, TPU, or even C, but these belong to classical hardware. So example are, I don't know, any large language model on a cluster of CPU on a data center, and so on. Image recognition on automotive processors, so something in autonomous vehicle, the image recognition reader and so on, technology and processing of image on board, or AI agents on edge devices. This is, of course, strengths can be we know neural network are quite general purpose, quite resilient, quite the inference is usually quite fast, but as a cons, they are mostly data driven. We need a lot of data. There are other problems to take into account, like the scalability, but also the security, accuracy, fairness, and explainability of this model, because we need to demonstrate that this model, the black box model, can have, we can learn something from the system, and explainability is something that, a characteristic that needs to be explored. Then the next category is, in my opinion, the most interesting among all other categories. So why? Because it's classical software on neural hardware. So we are talking, the idea of this category is that you have a neural hardware. So for example, an SNN based device, and we would like to run classical, traditional algorithm. So for example, we would like to run a bubble sort or any similar type of algorithm on a spiking neural network device. This is why? Just because this is theoretical, we are exploring this, but just because we know that these spiking neural network, for example, are Turing complete. And we started, so the challenge is on adapting this von Neumann programming, so this traditional programming, to neuromorphic computational domain. we started, so there are different levels by which we can approach this problem. One can be, for example, very low level, finding a sort of adaptation of the different structures. So the control flow, for example, a branch condition, a loop, and so on, according to Bohm-Jacopini, this or structured programming, and map it into some sort of neuronal motifs. So there are ways of by neurons to implement loops, convergence, switch, and similar. This is one. Another one is, for example, to try to map this an algorithm into a sort of graph and representing it as an optimization problem that then should be mapped into this spiking neural network system. Anyway, this is something that is, of course, still something that we would like to investigate. Last but not least is this neural software or neural hardware. Okay, this is quite common, let me say. Of course, in this category, we have neural hardware, so spiking neural network, for example, as we said before, based the device, Loihi, True North, or whatever. And we would like to run neural network software, so normally spiking neural network, but even more challenging is, for example, running on it some sort of different artificial neural network. Why not? So even this can be somehow challenging and interesting to further develop. But even if some of these, it's this, how to say, category has been already explored by the implementation, of course, of spiking neural network software on spiking neural network based hardware. The benefits, of course, as well as in the previous case, is that probably we are able this way to reduce, to be efficient, to implement an efficient algorithm, much more than traditional one, because it's shown that this spiking neural network based device can improve the energy consumption, can reduce, can limit the energy consumption. So, just to close my presentation, as future direction, we, as I said you before, we are mostly trying to working on this really challenging, how to say, classical software on neural hardware category. So we are trying to investigate mainly this category according to this couple of ideas I mentioned before. Why? Just because we are mostly inspired by this efficiency in general. Energy efficiency is one of the goal, but also in terms of performance and so on, we can have even resilience. We can have better, how to say, performance, if you want, than traditional classical in classical architecture. So the goal is mostly on implementing mostly all these paradigms, and mostly try to implement also case studies that are able to exploit these, especially the classical software on neural hardware and neural software on neural hardware category of case study, more or less. Okay, that's it by my side. If there are any question, I am more than happy to answer them.
Thank you, Salvatore. Great job. Okay, let's go to the QA session.
Thank you very much. Very interesting topic. I just had one question in the section where you're talking about the neural software on neural hardware, and you were mentioning the benefits. You mentioned, yes, great, thank you. The extreme energy efficiency and inherent parallelism. Could you talk just a little more about what you mean by robust adaptation, just to kind of understand better what that means?
Yeah, this is always related to this plasticity, for example. The idea, and this is something that we can exploit in classical software or neural hardware. So one of the most interesting aspects of neural hardware is that you can change not only you can adapt not only your system based on the, let me say, on the weights, if you want, but also structurally based on plasticity. Structurally, you can change the configuration of your, how to say, hardware in this case, if you are using neural hardware. That's why, and this is an aspect that, for example, is not present in classical hardware usually. So usually classical hardware, okay, you can implement some fault tolerance, and you can implement some switch and so on. But neural hardware in this case have this, I would say, further level of plasticity that implement, that allow and ensure this robust adaptation. So we are mentioning especially to this specific characteristic of neural hardware here, and even of course in the other classical software or neural hardware category. So this can be one of the most interesting aspects of exploiting the neural hardware.
Okay,
I don't
so
know
yeah,
if
the underlying architecture is a lot more opportunities to change the underlying architecture versus a classical hardware.
yeah,
Okay.
exactly.
Does that mean that if you were training some neural software that it's more stable than you might see on classical hardware, that kind of thing as well? Or is the like the
I say we have some experiments on this category. Of course, we are running some experiment on spiking neural network. Especially Max is an expert on this topic, implementing also real. I would say, especially focusing now on energy efficiency of these devices. So yes, the preliminary results are mostly shown that in this category, the main advantage is mostly, the biggest advantage is mostly on energy efficiency.
okay.
So especially in Max is doing also experiments on memristive architecture, especially those are really quite efficient in term of energy. So,
Great.
but yes, in my opinion, the potential is pretty much higher than it's not just limited on the energy efficiency. So this plasticity, but even we can, I am pretty sure that we can further push on this model in order to exploit, sorry for the noise, in order to exploit better the potential of this architecture. The real problem so far is, in my opinion, related to, for example, memristing in the miniaturization of this technology. So, as you probably know, memristors are still something that is not yet so simple to miniaturize. So we cannot have a billion of devices of memristors within a single circuitry, and this is quite challenging. But if we will be able to miniaturize even these devices, and these we will that it will be a really good solution, because overcoming, as someone said, the Moore law and the von Neumann architecture, how to say, wall, that are quite well known so far.
Very exciting. Thank you so much.
You're welcome.
Thanks, Dr. Sean. Someone else? Oh, okay. That's all. Thank you, Salvatore.
Thank you, everyone, and have a nice continue of the conference. Thank you.
Thank you so much. Okay, let's continue with the next talk. This present by Victoria Popova. Victoria, are you ready?
Yes, good morning, everyone. Share my screen. Do you see my screen?
Yes, we can just try to talk a little bit higher, please. Go ahead.
Sorry. First of all, thank you for giving me the opportunity to present my research. And today I want to talk about the problem what we often underestimate in artificial intelligence, just because we tend to trust the model if it achieves the higher accuracy, but in reality, two models with a identical accuracy can have completely different internal reasoning process. So one of them, for instance, might be unstable and incoherent or even dangerous in critical applications. So my work proposes a framework called Gravilogic, which treats AI reasoning not as a static point, but as a dynamic geometrical trajectory in latent space. So this allows us to measure the coherence, smoothness, and stability of AI reasoning, essentially to look inside the model's thought processes. So I'll work you through the problem, the limitations of existing explainable AI approaches, and the key idea behind Gravilogic, of course, and some results showing how this method can review differences that accuracy alone can capture. So let me give you a quick roadmap of today's talk. First of all, I'll explain the problem. Why accuracy alone can be misleading. And then I'll show you the key limitations of current explainable AI methods. So next, I'll introduce Gravilogic, our approach to modeling AI reasoning as a dynamic trajectory in latent space. And finally, we'll let you know what this means for AI trust and reliability. So here we face the core challenge in AI reasoning, it's opacity. Like even state-of-the-art models often deliver high predictive accuracy, but remain a black box in their decision making. So in practice, it means, well, we see the answer, but have no idea how the model got there. So in high stakes domain like healthcare, finance, or law, understanding the rationale is just important as getting the current prediction. So for instance, imagine like the medical AI recommendation about surgery, but without knowing its reasoning, you would not trust it. So the lack of transparency creates real risk in many domains. It can conceal biases, both systematic and social, like making discrimination invisible, for instance. In the same time, it can undermine human AI collaboration because people won't trust or effectively work with a system they can't understand. And finally, it can complicate like regulatory compliance, for instance, GDPR in Europe. And here the key challenge is that most interpretability tools today focus on outputs, so highlighting important features for a specific decision, but they offer a little or no insights into the reasoning process itself. So the actual path the model's thoughts like takes from input to output, and this gap is exactly where our approach Gravilogic comes on. So most popular explainable AI methods today, like Lime or Sharp, unfortunately static or local. and they explain one decision at the one point in time, but ignore the entire reasoning path. So this gap we're trying to address. And still, like Lime and Sharp today are the core tools we have, and my approach does not aim to replace them. Instead, like Ravel logic complements them by ending a dynamic view. So reasoning and capturing how decisions evolve all the time in latent space. And together, if we're gonna combine many of them, it's what I'm trying to do, they provide a fuller picture of model behavior. So, but before we dive into the method, let's first understand why these even methods. Like, so the ultimate goal of many AI systems is not just to output correct results, but to mimic human-like reasoning. And I think it's obvious that human reasoning is dynamic, so we integrate new information step by step. And machine learning models, although plurally mathematical, of course, they perform a sequence of progressive internal transformations. So if reasoning is truly a process, then our method for explainable AI must also be a process oriented. So allowing us to trace the entire trajectory, not just inspect the final answer. And the topic is essential, relevant for the BICA community, because our focus is not only on building functional AI, but on understanding and modeling the underlying cognitive processes. By treating AI reasoning as a dynamic tragedy, we align more closely with cognitive architectures and neuroscience-inspired modeling and studies of human decision-making, of course, and all central themes like for BICA. And this bridged the gap between engineering metrics and cognitive magnificent evaluation of AI systems. So the name gravilogic comes from the analogy between reasoning in latent space and motion under gravity, where invisible forces and curvature shape the path, just like in physics, and important masses and the data bend trajectories. And reasoning tends to follow smooth or optimal roads. So to capture this, we must leave the service level outputs and move into the latent space. So in latent space where the actual geometry of reasoning unfolds. And there is only one place where coherence and stability can be directly observed and measured. And here you can see the example from the breast cancer dataset, comparing reasoning paths between a healthy case, it's blue, and a malignant case is red. And each subfigure shows the same case pair, but projected into different latent spaces. The first example is PCA, aligned projection, preserving large-scale variance, and the path appears almost straight, as you can see. And the second one is outer coder, like aligned and nonlinear and bending, making the space more compact while keeping the reasoning path short. And the last one is manifold preserving method that reveals more curvature, like moving how the reasoning process navigates complex logic geometry. So despite this difference in geometry, like the overall coherence of the reasoning trajectory is preserved. So meaning the internal logic remains consistent across embedding. And if we stay in an original feature space instead of a latent space, we risk missing the actual geometry or the reasoning process, because in raw space, there is a high risk that some features can affect or correlations between our features can affect So it's better to go to latent space for it. For instance, SHAP works in the input space and tell us which features are important for a single prediction, but it does not tell us how the model internal representation evolved over time. So it moved smoothly toward the decision or jumped chaotically between states because there is a huge difference between them. And in contrast, working in latent space lets us to track the tragedy itself. So here, for instance, you can see the reasoning path goes from point A, it's our original input, to point B, it's our counterfactual point, just across the decision boundary. So in other words, we ask in the model, like, what is the smallest change that would make me change your decision? And this matters because it shows how sensitive the model is near decision boundaries, and it helps spot cases where the decision flips to the wrong reasons. And also, it led us to see if the path is smooth and direct or unstable. Yeah, in a gravity logic, uses counterfactual points like markers, and they help us check if the reasoning stays stable and consistent. Here you can show the reasoning example with gradient boosting model trained on income dataset, each colored line represent the change in predicted probability as the model moves step by step along the reasoning path from the starting counterfactual point toward the original input. So what we see, all models had achieved like very similar accuracy on traditional metrics, but as you can see, the way internal reasoning paths looks very different. So some paths are smooth and monotic, but others jump a lot. So why it's matter? Again, just because two models can give equally good final prediction, but the stability and coherence of the reasoning process behind them can be fundamentally different. And even through gradient descent, you can say like gradient descent trains the model, and it does not explain how the model reasons inference time, but the training can be smooth, but during inference, the reasoning path may still have sudden jumps. So those jumps are not caused by training itself. They come from the model moves through latent space and make decision for specific causes. And they happen due to latent space curvature and strong feature influences or decision boundaries. So gravity logic helps detect these jumps, showing they are not noisy, but structural patterns in the model's internal logic. So recognizing them is a key for trust and interpretability, of course. And there we can see two models with the same accuracy, but with very different reasoning. As you can see, the red path jumps sharply, showing unstable decision-making, while the green progresses smoothly and reflecting consistent. Here it's the key metrics, like how we really calculate it. Those metrics are still experimental, that they are developed empirically based on observing many reasoning trajectories across different data sets and models, and each metric is designed to capture the distinct property of reasoning quality. Latent path line is how far the model travels in latent space. Our second metric, like output change, it's how abruptly it predicts change semantic smoothness. Looks at the continuity to meaning along the path. Curiosity, and of course we have gravilogic score. Gravilogic score combines them multiplicatively. So a low value in any of dimensional lowers like the overall score. And the reasoning behind this design is that good reasoning should be short, smooth, semantically coherent, and geometrically stable. So if any of those competence is weak, the reasoning process may be unstable and we can't really trust it. So to conclude, the Gravi logic framework is still in its early development stage, but the first results show that it can uncover differences in reasoning quality that traditional metrics completely miss. I can give another example, for instance, about financial risk model. The two clients with almost identical profiles, for example, get opposite credit decisions, and counterfactual analysis reveals the model relied on tiny, so irrelevant change in data. And there are the kind of cases where measuring the path of reasoning, not just the final prediction, becomes essential. So our next steps are to test gravilogic on a wide range of data sets, of course, refine counterfactual generation, and of course, improve our theoretical basis of the metrics and explore integration with cognitive architectures. So thank you so much for your attention y muchísimas gracias por darme la oportunidad de presentar mi proyecto.
Thank you so much, Victoria. Attendees, does anyone have a question? Okay.
Thank you very much for your presentation. I think I got the basic idea. You want to apply reasoning not only at the end, but during the decision making.
Yeah.
Isn't it correct?
Yeah.
Okay. Now, what I missed or I didn't understand or I didn't see is this. When we say reasoning, usually we mean that we apply a function and this function satisfies certain axioms of logic. I haven't seen them. Could you please elaborate on that? Thank you.
You mean you want to see how the function moves from outcome to...
Yeah, what is reasoning? Can you show us what you call reasoning? What is the reasoning process? How it is enabled?
Yeah, so basically our first point is A, and our B, it's our counterfactual. So we moving, for example, we have two types of clients. The first person we need to accept the credit and the second one, no. So it's gonna be our point 1 and point B, and we're gonna change some features to explain how is clients working, for example, to understand how exactly the model thinking to understand who gonna be our client, for example. So in my framework, by reasoning, we don't mean formal logic with explicit axioms. So we're trying to define its sequence of internal representation, like to changes that the model goes through, then moving from an output and to decision. And basically, we sequence trajectory in latent space. It captures how the model integrates evidence step by step. So the quality here, quality of reasoning, it means like whether this path is smooth, coherent, and stable or not. and rather than wherever it falls symbolic logical rules. So it's a geometrical and protest-oriented definition of reasoning, not a symbolic one.
Thank you.
Thank you. Does anyone else? Oh, okay.
Hey, thank you for your presentation. I just got, I think, a little bit confused because you said that there is a chart that you showed that has like this lattice space representation over time, but I didn't understand so well. What are the points there? The lattice space is changing during like inference or like during training? I didn't understand how well the method works. Not the method, but also actually the analysis.
Yeah, thank you for the question. You mean the picture when I was showing the three pictures of different latent space?
Yeah, exactly.
Okay, so the latent space we show is fixed like after training, so it doesn't change during inference. So the changes are the positions of points along the trajectory, and when we interpolate like between the original input and the counterfactual input, each point like represents an intermediate state,
Oh, okay.
internal representation, I mean.
So you're doing some kind of perturbation analysis in the input and trying to figure out the like the topology of the latent space based on these perturbations.
So basically, yeah.
Okay.
But I can think of it's like a form of how would it say, like instead of only measuring the effect of the output, yeah, we tries to show like how this controlled how you call it, like perturbations like moving from the original input toward the counterfactual, yeah.
Okay, thank you.
Thank you very much. This is a very important topic, and I appreciate you investigating it. I just had a question. So, related to going from, these latent space representations to more something like an explanation, it's not clear to me. So, you had some metrics that kind of characterize the smoothness of the latent space and the distance, the path distance between different points. How do you, unless you already know for one of these higher dimensional representations what each dimension means, like a disentangled kind of representation, how do you go to a human understanding of the reasoning process without first having dimensions in your latent space that are already understandable?
Thank you for the question. First of all, there is a very important point that our metrics do not assume that individual latent dimensions are directly interpolate to humans. Instead, they treat the latent space as a structured manifold and focus on geometrical properties on the trajectory. So line, curvature, like smoothness, which are model agnostic. So there's properties can be compared across models to access reasoning stability. And talking about human understanding, we see this as a complementary to attribution, like or attribution can tell you which features matter. So while our metrics tell you whether the model use of those features is coherent and stable over the decision process.
Okay, so are you kind of characterizing the latent space of some algorithm overall versus, so for example, you had autoencoders. So if you go to autoencoders to variational autoencoders, the space will be smoother. Is that kind of what you're trying to characterize, the latent space characteristics?
So not exactly, because we are not trying to characterize the Latin space or the architecture in general, but the specific reasoning trajectory for the given input to controversial pair, the thing like that space. So different embedings here, like outer quarters or others, like they can change the geometry. So for instance, some of them, probably I can say, can yield smoothly manifolds, but we need to test it to understand better. But our focus on the relevant model's decision-making path remains coherent and stable across embeddings. So not on benchmarking the embeddings themselves, mostly, yeah, by the specific reasoning trajectory for the given input to a counterfactual pair.
Okay. Thank you very much.
Thank you, Doctor.
Okay, thank you so much, Victoria, and congratulations.
Thank you.
Well, let's continue with the next presentation that will be performed by Mohamed Ezat. Mohamed, are you ready?
Yes, I'm ready.
Okay, go ahead, please.
I want to thank BICA for giving me the chance for presenting the latest finding in my research. I am Dr. Mohammed Izzat. I'm presenting atom concept. Atom concept is about atomicity that unifies the perceptual and the cognitive, that reconciles the semantic, the symbolic, and the connectionist for constructing self-evolutional agents. The best way to start the presentation is by comparing the proposed atom concept with the well-known artificial neural network. We'll start by the atom neural network, which is one of the constituents, the neural proposed by the atom concept to complement the symbolic constituents. Artificial neural network is known as statistical pattern learning for massive data, while atom neural network is meant to support agentic self-awareness. For the artificial neural network, there are always specialized versions that may target vision and language, and a struggling variant for spatial interconnectivity. For atom neural network, we depend on something called meaning, which actually implies the invariance. Invariance, we will materialize it using group theory. Doing so guarantee that the material, the immaterial, and the multimodal representation may be unilaterally represented by the atom neural network. The artificial neural network depends on concreteness. Each entity should be represented by a concrete vector embedded in a Euclidean space. For example, CLIP would unify the vision and language, which is used in many applications. But for the atom neural network, it depends on abstraction. Entities here are abstractly represented, and this is reasonable because we are actually depending on group theory representations. Atom concepts come in two flavors. One is the symbolic, which the specially designed atomic propositions, along with the proposed atom neural network for the connectionist variant. The concreteness of the atom neural network implies that the measurements between these concrete samples is measured to metrically measure the closeness between these variants, while the atomic neural network proposes something called the relativistic comparisons. While there is always a descriptive space that lays between two extremes, the -1 and the +1, over which comparisons between entities, the comparisons here depends on structural comparisons between two extremes to lay out this is special for comparison, which actually leaves the road for mimicry, which means that it's a shift in paradigm. Mimicry is the first thing newborn infants actually are capable in doing. Consequently, the artificial neural network has to come in two conceptual processes. One, training, which defines the transformations occurring over the coordinates or the concrete example of the vectors representing the entities. While for the atom neural network, these two processes are actually intertwined. Each of these are aware about the others. They are mutual development between these two processes. Let's take a look at the nodal structure. Nodal structure will give us a better understanding of the differences between these two entities. Again, we are comparing between them just to have a clearer understanding of what the atom concept stands for. Atom neural network activates non-linearly activates on the certain inputs, while the nodes of the atom neural networks are actually simulations. They are gamifiable, geometric algebraic local simulations of the verbs. Each of these nodes are just a verb environment or an event structure that simulates the arguments and their interrelatedness with the parameterization occurs by the verb. When the link is spanning between different verbs, it structures what is known as the atom neural network. The weights here are just relating the arguments in these environments. So actually, we are like linking separate scenes, separate geometric algebraic scenes together to construct hierarchical paths linking the atom neural network. The atom neural network is at the same time a graph, meaning that it's searchable, and it may stitch these neurons may stitch together, and the features are automatically discovered to construct the long-term memory, while it maintains the capacity of the manifold based local simulations in contrast with the atom neural network. In summary, atom neural network comes as a black box, while the artificial neural network, while the atom neural network comes as a combination of atom proposition, the symbolic variant, along with the atom neural networks. It supports the variants of states, processes, embodiments. These three entities are guaranteed to be modeled by the atom neural network. This implying that the black box of the ANN would transform or process concrete examples, while the atom neural network actually acts on systems and the processes. Based on that, we are going to structure the presentation. We'll start by presenting the atomic propositions, which is the symbolic variant proposed by the atom concept. It will follow by the atom NN. Most of these consume what we propose to reconcile the symbolic and the connectionist theory. Then we will construct agents, biological agents that actually will be very much contested concurrently to construct, which will come very easily using atom network, because we are actually, if we look closely at the atom NN, it's a model of a neuron. We say that a neuron is a scene, is an algebraic geometric scene that is gamifiable over gaming engines. To have a closer look at the atom propositions, we have here the states along with the change. Change is the verbs, environment, and the states are represented with the proposed atom propositions. When we say atom propositions, we mean the arguments of a verb. that it changes but parameterizes the parameterization of the verb is fixed, and it parameterizes the stage with the help of the observer. The observer actually is the one who is linking these variations together. To define meaning, this is the conclusion of my PhD, which I actually it goes through several publications. It was translated into several languages. The theory states that three perspectives are sufficient to explicate all the variants of any entity that is material or immaterial, and these three perspectives define the open classes of language, along with the proposal that defines the arguments and the verbal structure and the description of the observation. The closed classes construct the dimensions, the open classes the material, the arguments, the behavior, the verbal parameterization, where the observation is both the speed of change that linking the parameterizations of the verb along with the features of the argument. The closed classes comes in the connectives in three flavors from each of the three perspectives. The adpositions, which are actually argued by many of the prominent cognitive linguistics, that it is the main thing that structures the open classes, and this is actually what the paper proposes. The adpositions were distilled into 7 symmetric dimensions, x0 for the spatial relatedness, while x3 for the directionality. The reasoning, the if-then statements, which will be vital for the proposed model, have a dimension fits all, and the describability has dimension x2. This is the comparison with the +1, the 0, 1. The x4 is for modeling swarms. These two product by SO3 cross XO3 would hierarchically actually tend to model swarms. The last two dimensions model geometries, the first Fourier representation of geometric interpretations of the materialization of these abstractions. As an example of how these dimensions may be materialized, we may see that just an on adposition maybe have the fixed type and several instantiations for A on a table, or A on a wall, or A on a ceiling, and all of which would maintain its clarity, spanning any variant of natural language instances. The same applies for all the other adpositions. And from this point on, we may actually desert the idea that it is adposition dimension. That's it. It's from now on, it's just mathematical abstractions that are going to be used as the main constituents of the atomic propositions, populating the arguments of the verb or the event structure. To have another look just to the state changes that we described earlier, we have the state change. The state now is populated by the atomic proposition. These are the arguments of a verb, while the verb itself is represented by SE3, the special Euclidean group, which has actually the two subgroups of rotation and translation. The parameterization of these subgroups would parameterize all the arguments of the scene. When we observe the delta, or the change of these variables in relation to the argument, and actually we assign this, we enter comparability over the descriptive space, which is learnable because it's differentiable using backpropagation, the variant of backpropagation. For the atomic neural, for the similarity comparison, we may compare the paths linking. These are nodes. Each node present a scene, a 3D scene, or a verb state, and the linkage between them represent the if-then propositions, and we compare between them based on different variants to transfer learning the similar patterns. For the atomic neural network, for A at the upper left, we find that actually it comes in to explain the relation between any two entities. So to explain a relation between a hammer and a nail, or a hammer and the door, would have like a path between these two elements at the linkage to explain these relations. Nonetheless, this temporal domain is translated by B into two planning space and an execution space, all of which are represented by spanning the verb space. The process here is to find a verb, like a statement, a simple statement relating any two entities, and out of this verb space, we would emerge a planning phase and an execution phase. If we look closely at how this may happen, we have a verb that join these two arguments, and based on that, the linkage between this linkage is hierarchical, communicating the arguments in a simulation scene to arguments in another simulation scene, ultimately building what is known as the comparative space. As a variant of this constituent, we may find that the hierarchicality actually of the neural network may manifest over the two execution and the learning spaces. We'll have here the lower, the execution space, as the fine ingredients. These objects are actually gradually integrated into the verb that joins the two entities to summarize the relationship between them. And several processes may occur over these variations. We may actually, these fine ingredients may be just summarized and used in the left diagram as just a comparative. We are comparing this fine detailed library. It's like a library of fine details to come up with certain comparisons. We can still process different processes to inhibit or encourage certain impulses between the relationship between these elements. All of these are differentiable, and actually it supports a white box biological like backpropagation. How to apply this on an agent? We have here two constituents: a 3D scene and a link between the scenes. This link that spans the argument in the different scenes is known as the if-then. For an agent to benefit the proposed atom concept, it would come up with variants that do actually populate these 7 dimensions. All of these can be populated using either language instances or gamified scenes, or of course vision references. The self-awareness here may be built easily on, there are several interpretations of how self-awareness may be done, and these may come in ease using the comparison spaces to prove that, or to explain that if the agent is capable, or how it may be, how it may get affected by the world. As an example that actually signifies the importance of modeling a neuron as a geometric scene rather than a nonlinear activator of the ANN, we may find that the C. elegans have only 302 neurons that are responsible for all the actions happening in these networks. We may actually experiment with the proposed atom neural network and the atom propositions. First, by construction, we define the neural hierarchical structure, like the parts responsible for the motors, or the parts responsible for the other sensorial and other parts of the agent. And it has to come with the fixed wiring, because the wiring here, we have a neuron. The dendrites of the neuron should be actually feeding the argument of the inbound of the SIM, because each neuron has its own simulation. When we construct an agent here, the sensorials or the motor-based actuators will be critically linked with within features.
2 minutes, doctor.
Yeah, okay, great. It's about to finish. After that, we have two phases: the development prototyping, which actually both of these defining examples, because we are mimicking and differentiating to mimic certain examples. So we come up with examples like giving a higher level hierarchy examples, or a relation between a higher and detailed ones. And based on that, the agent will be left to self-develop, and then revised to check for its robustness and reliability. In conclusion, the proposed atom concept comes in the two flavors of the atom concept and the atom neural network, that both of them would support self-awareness of the agency. They deal with the trilogy of state, process, and embodiment observation, opening the door for modeling of the systems, either internalized systems or externalized systems. Each of the atom concept actually of the dimensions come equipped with because actually the speed of variance of each of the changeability over these dimensions comes somehow equipped with mechanical simulations to just model the resistance of the mass or the effect of the forces. And interesting results would come by modeling the general relativity and quantum field theory spatial fields over the general Bilbus manifold proposed by the atom concept. For the future development, stochastic model, atomic model may be proposed, which actually comes very friendly with the proposed descriptive +1 - 1 group. Nonetheless, by stochastic modeling here, it's the if-then statement, and the controllable swarm of AG agent is under investigation. Thanks a lot.
Thank you, Dr. Mohammed. That's was impressive. Well, does anyone have questions?
Thank you for the presentation. Very interesting. I have one question regarding, have actually two questions, but the first one is, what optimization process are you using? because in, for example, neural networks, we use stochastic gradient descent, and I think I didn't understand so well what do you use like for learning in your neural network?
When I learned when the learning procedure is always a description between you have to pick an extreme, and when we say mimicry learning, we want to reach this extreme. The extreme is represented as a atomic proposition, or as an if-then statement, the one that spans the different scenes. And to reach this maximal point, you have to have the infinitesimal changeability of its the proposed constituents of that you think that it actually may constitute this optimal goal. and the optimization process would just optimize this infinite small to get the concept that you have as close as possible to the extreme. And actually, the defining extremes is a foundation for defining free will, because free will, according to the research in hand, says that the free will is the definition of the extremes. It's like you define your idol, and based on the idol definition, or the thing that you think is the highest, you do your best to reach this highest. And this may be a part of the free will, but of course, for low-level agents like the fruit flies or the variants that presented, there will be no free will. We will always define the extremes, the goal that the agent had to seek. And this is how actually it learns. So actually it supports the gradient descent. It's aware. There is always the entwining, as you said earlier, because it can search the graph and it can know where it changed and where it did what and what is the result of doing so. There is other variation that it's proposed in the paper that is the genetic generations. This is the evolutionary algorithms, because actually the proposed model is symmetric. There is always A and the inverse of A. The inverse of A is not the mathematical thing that we think. Actually, the orientation of the whole thing depends on when you say A, what is your not A. And it's the one you know what is not A, you are totally aligned. The two conversant, the two agents involved in the conversation would be totally aligned. Okay. And based on that, the evolutionary algorithms are proposed in the paper.
Okay, thank you. I just got someone have like more questions.
Thank you for presentation. A very quick question. The input and the output of your atomic neural network, are they discrete or continuous? Thank you.
The dimensions that proposed, the symmetric dimensions, 7 dimensions, and their cross products that proposed to represent the atomic propositions, they are continuous, but they of course support discrete subgroups, because the cyclic and the hydrant subgroups of the SO3, along with the solid platonics, are discrete. So there could be discreteness implied in the situation, but this discreteness is coordinated with the manifold of the Lie groups. The inputs here, and this is the challenge of the atom neural network, the input here is you question the neural network. You may come in any node of these scenic nodes and find links between these nodes to come up with a certain query. And based on the simulations, you would come up with the answer to this query. So this is one of the many strengths of the proposed atomic neural network. It is not fixed in the feature. The feature space is not fixed. And the conclusion is based, it's like there is always an ongoing discourse between the neural network and the conversant, the one who is conducting a conversation with the neural network. This means that an optimal energy conservation would be is paralleled with the atom neural network, along with the efficiency of this atom neural network. Actually, it may fit a fly-sized robot as much as a fighter jet sized robot, and both of them will be communicating invariably and reliably in a coherent process between these two areas. So this is actually a main part of what drove the the notion of this whole project.
Thank you so much, Mohammed, and congratulations.
No more questions?
Okay, let's
Thank you.
continue with the next presentation.
Thank you very much.
Our next speaker is Milin Kodari. Milin, are you ready?
Hey, hi. Yeah, I'm ready. So just a second, I'm sharing my screen.
Okay. Well. Okay, let's get started.
Sure, 1 second. Is my screen visible to you guys?
Yeah, we can see your screen, so go ahead, please.
Sure, just a second. So, by the way, I'm here with one of my colleague, Dr. Gunjan. She was a part of this paper. So she'll start the introduction part and then I'll carry on. I think sounds good. Yeah, go ahead.
A very good morning to one and all. And we are sincerely thankful to BICA for letting us present our work today. And this is Dr. Gunjan Asrani, and I have my colleague Milind along with me. We'll be presenting our work today. So our work is real-time rendering of physical environment to the robot mental model using Unreal Engine 5. So this is the phase 1 of our work. We have our adaptive cognitive robotic architecture in place, and there are two related work which we have done till now, and this is the extended work of the robotic cognitive architecture. Moving on, this will be our agenda for today. We'll go through each section one by one, and then Milind will take over in the between. And I'll start with the introduction section. So at present in technology, there have been rapid advancement in robotics, but despite those advancements, most of the robotic systems rely on static maps and fail to perform in dynamic, unstructured environments. What we are trying to solve this problem by implementing uh, uh, like uh, real time reconstruct virtual reconstruction framework, and this framework helps to continuously update the internal model inside the robots like humans, so that the robots perform like humans by continuously updating the surroundings into the mental model of the robot. So basically it creates a picture or mesh of the surroundings of the physical world and renders it into the virtual world, which is the robot, which then goes as the robot mental model. And that is the reason, since it continuously updates the surroundings and implements it into the robot mental model, it is highly helpful in performing in dynamic unstructured environments. So that was the whole goal and motivation behind this project. And moving on to the next section, that's the related work. So at present we have published we have already done and published three of our works in these three categories, and this is the advanced version of the work which we are presenting today. And the first one which we had already implemented is the MMD algorithm, which stands for match mediated difference algorithm. Now this algorithm helped us to create these synchronized visual fields and helped us to create the differences, or let us know the differences between the real and synthetic videos. But it did lack the 3D reconstruction capabilities. And this is what our extended work is today, where we are implementing the 3D virtual reconstruction framework with stereo camera and Engine 5. The second of work which we had already done is cognitive robotics research, which the like few minutes back when I was talking about rendering the physical world and creating a mesh of the physical world and rendering into the virtual robot mental model. So that entire rendering and simulation, that part, the rendering, research rendering and the simulation of the physical world, that was the part of this cognitive robotics research. And the third, which we had already done, was real-time spatial mapping, which creates a 3D mesh or map of the physical world and surroundings, which gives us not only the depth but also the geometry in detail, like higher hierarchical level of detail, using the RGB and the depth map. So this is what we had implemented, and this one goes beyond the SLAM architecture, which is the simultaneous localization and mapping. So this one was little advanced than SLAM. It helped us to create a real time 3D map of the surroundings. And now what we are trying to do is to create the 3D virtual reconstruction framework and implement and rendering it into the virtual world as the robot mental model. So moving on, now we'll start with the specifications and hardware configurations and approach for a project. And Milind will take over from now. Thank you.
So I guess panel, I guess you all are now good within the understanding why are we doing this project, and this conference, this paper which we have done for this year at BICA is basically how we are doing it, and how is it possible for everyone out there who wants to create their own mental model for the robots to think and act like a human being. So that's what we're trying to do, and this is the first phase. We have multiple phases of this project going on. So this is the first phase, and the hardwares and configuration which we have used here, like Z camera, it's a stereo camera for RGB inputs, and we have used the ZSDK and along with that Unreal Engine for creating the simulations and the virtual environment for the robot. Then we are moving further. Like that, Unreal Engine is also configured using the Visual Studio in the C++ language. That was also the part of this project. So the actual approach of this project is like we will be using a Z camera, a camera with a stereo camera, which captures the image of a room or any environment instantly, and create a mesh, create a point cloud, combine the point cloud and mesh, and create a virtual environment using the Unreal Engine's capability and the plugins. We create a virtual environment instantly, not with a lot of latency. So what happens nowadays, like in SLAM or in the traditional architecture, it happens like once a lot of people will go with the camera and speakers and lidar and radar on the roads, and they will map everything and then come back. They put the robot in there, and they mention the robot like you are standing here. Then starts the SLAM architecture. But now robot doesn't know where exactly it stands. It doesn't know what exactly has happened. So when we do the mapping, after 2 days or 3 days, maybe there's a construction. Then robot doesn't know that that there is a construction, there is a barrier right now, but it can go in the same way which has been stored in the mind. So what happens now? It will be real time. It can directly see. So using the point cloud renderer and the spatial mapping manager, we made it possible to merge both of these inputs and create a combined approach. And then in the later phase, we can create a basic static virtual environment, and after that dynamic. So that's what the progress of this project. So I'll go one by one. So the camera initialization is one of the initial part. Then after that, we will be moving to the spatial mapping. Then it's the mesh updates. Then we have the point clouds. So after that, we will be combining with these two, and you can see these two, and you can see the combined update of the real world into the virtual environment that is in the Unreal Engine. So these are the few blueprints which you see. We have our project named as a dynamic rendering, and these are the few blueprints. The BP means blueprint, and the point cloud renderer, the spatial mapping indication, spatial mapping manager, and spatial mapping mesh, and mesh customizable. So these are the few most important blueprints which we use in Unreal Engine. So Unreal Engine has two approaches. One, you can create scenarios using the blueprints. Another one, you can create scenarios using the C++ codes on the Visual Studio. So we use this time as a blueprint approach. If things goes really well, like as of now it's going really well. It's if there will be any problem, then we can switch back to the C++, which will give us more diversity and more more room to play around. So that's what the approach is. So moving to the next slide. So this is the real-time world synchronization. I already talked about it. The data capture happened in the update loop. So there is a update loop, which has been created by our team, me and Gunjan, along with our professor. So we have been doing in the lab that thing. So that loop actually is created by the blueprints. You will see in the next slide what exactly the loops look like. The blueprints where we have all the tasks in a pipeline, and captured, and it performs automatically once the Unreal Engine is in the play mode or the start mode. So this is our basic architecture of this project. So Z plugin with the Unreal Engine, then we create the point cloud and the mesh. Then we integrate the point cloud and mesh together. Then there will be granularity management, which it is important for our project because we want it to be real time. And for real time, we need to configure a little bit, and we need to play around a little bit with the quality of the inputs or the images or the recordings which we are having, because high quality can delay the results, but low quality, which or maybe the sufficient quality or sufficient number of information which is required only for the robot to perform task, uh, will make it more efficient in terms of time, in terms of thinking, in terms of acting. So that's why we have this granularity management as a very much important part of this project. Then it goes through the blueprint loop. Then we create a real-time virtual environment. So this is the whole concept of the full project. So as of now, we have done to the mesh creation and the point cloud creation, and integrated the point cloud and mesh. So this is the custom loop which I was talking about in previously. This is the custom loop looks like in the blueprint in Unreal Engine system. Uh, so it has multiple parts. The first one is initializing the camera for the mesh actors. The second one is the special mapping manager. Then here is the execution part and integration of the both mesh and point cloud. So this is it looks like. Then we go next to the results. So here you see I have two pictures. One is for the screenshot with the live camera feed, and another one is the combined picture of the point cloud and the spatial mapping, the mesh we created with using the camera. So this mesh creation and mesh and point cloud update, the integrated update, is very fast. As per our results, we observed for each time we were observing it for the 5 to 10 minutes, and we observed that it was like 45 to 55 fps frame rates were there for the spatial mapping. And the refresh rate was somewhere in between 200 to 225 milliseconds, which is somewhere around 5 to 10 hertz per second. So this is a really impressive result which we saw. But it can be a problem when it goes to the live environment, when it comes to the scene creation in the later phase. So we are figuring out that thing, and it will be figured out soon, like how we can implement into the scene creation. So that plugin is already ready, and we will be doing it soon. So now a lot of things are in the future work we have right now. Uh, as a future work, as I told you, it's happening for the static image. The future environment is like we will be putting the robot or the camera into the dynamic environment. The scene will be moving, and the camera will capture the meshes and the point cloud in real time, create the scenes in the Unreal Engine system instantly at that same moment. And the second thing, we were thinking like if we can manage the granularity, if we can manage the objects in the room, like if a robot wants to go out of the room, it should only recognize the path, and the second thing will be the door. So the target should be that minimal so that robot can render everything very quickly and very fast, and it can go outside the room instantly. So that is the second cognitive rendering we have to we are going to do it in future. And the third is like AI integration. Definitely this whole system we are creating for implementing and testing the AI codes or AI algorithms or machine learning concepts which can be implemented into the real robots. Before putting it to the real robots, we want to test it in the environment of the simulation. So that's what the main purpose of building all this whole system is. And we will use the YOLO algorithms for the object detection so that it can recognize what things are important for it, what things are not important, ignore them, and render them. So like that. So this is the whole concept we have. And in conclusion, we will say, like right now, the 3D reconstruction is we have initiated already. The mesh and point cloud has been generated already with a very low latency, and we can merge it and we can create a whole skeleton of the virtual environment or virtual world uh, in the live at the live at a live camera. And we are able to create some a little bit of a little part of the mental model of the robot. So and this is a very scalable foundation that we see, like it can be a very
Future.
scalable project for the future, for any kind of industry, for any kind of uh, industry which will involve in any physical AI or the robotics or the any computer vision also. So it can be very useful there. So that is the conclusion of this phase one, which we have completed uh, last month. And we are very thankful to the Pace University and again the Office of Naval Research, who has been supporting since start for this research, and definitely our Professor David Benjamin, so who has been the mentor of this project to us. So thank you so much for your patience, and I think we are good for the questions.
Thank you so much. Amazing work. Okay, we have a question here.
Yeah.
Uh, Thank you for your presentation. I would like to congratulate you. My point of understanding is that this is a preliminary work to a major project. So this is the first step, so to say. And if this is the case, I would like to ask, what is the resolution of your image in terms of millimeters or centimeters or whatever? What is the resolution of the objects you represent?
So thank you so much for the question. So we capture all the images and the videos or anything through the camera. It's coming in the 720p pixels resolution. So that is the resolution of the images and any input we are capturing there.
Talking about the resolution of the real world, for example, can you see an olive, a small object?
Yeah.
Can you can you see it? Can you represent it? Or you can represent only tables and chairs and walls?
Static
Okay.
objects. Yeah.
So coming to that point, so right now, as you see, as we mentioned about the meshes, mesh and point cloud can see every single object, small to the larger right now. But our focus is not for this project, the whole project. We are not focusing on the small objects
Okay.
because we are focusing more into the time efficiency and how easily and how efficiently it can render. So that's why we will be focusing more to the relevant objects, a bigger or the smaller, whatever it is, relevant objects for the robot's task.
So I would like to add, so for the time being, our goal is for this phase one, our goal is to create an adaptive, high fidelity, and low latency network or reconstruction model, which can be helpful for the perception driven reasoning for the robotic architecture. And once this is created, once we have the map in place with very low latency, for example, the latency right now is like 200 milliseconds, lower than that, so we are trying to achieve lower latency. And then once this is done, then we'll be focused more on the localization of the object and the resolution which I think the direction is into that area. Thank you.
Okay, we don't have more time for questions, so thank you so much.
Thank you.
Thank you so much
Thank you so much for letting
your
us present our
attentions.
work.
Thank you so much.
Well, thank you for your attention. I have the pleasure to introduce the Professor Run Sun. He's a cognitive scientist who made significant contributions to the computational, psychological, and other areas of cognitive science and artificial intelligence. He is currently known for his work on the Clarion cognitive architecture. He has published more than 115 technical papers in journals such as Psychological Review, Cognitive Science, Artificial Intelligence, and Neural Networks, as well as 12 books by Mid Press, Cambridge University Press, Oxford University Press, and so on. Ron Sun is currently Professor of Cognitive Science at Rensselaer Polytechnic Institute and was more formally James C. Dowell Professor of Engineering and Professor of Cognitive Science at the University of Missouri. He received the PhD in 1992 from Brandeis University. Thanks for coming, Professor.
Thank you for the introduction. Okay, so I would like to discuss the purported differences between AI and human intelligence, as discussed in philosophical literature, and examine that issue through the lens of computational cognitive architecture in relation to those notions discussed by philosophers, for example, rationality, intelligence, and so on and so forth. Let me get the pointer. Oh, okay. Thank you. Next. Okay, so one issue that confronts both technical experts in AI and computer science and the laypersons alike is the purported differences between AI and human intelligence and how one may close that gap between them. This is not an entirely new issue, yet it's important both intellectually and practically. Intellectually, it is important for the sake of better understanding of AI, and practically, it's important for better guiding the applications of AI. This issue has been discussed and debated by philosophers for decades, starting from, for example, Driver's 1978 book, What Computers Can Do, and John Searle's Chinese Room paper in 1980, and Dreyfus Brothers' book on human intuition, and also Floridi, Gonzalez, and so on. This question involves many important theoretical issues that I will get into briefly today. And there are also many new relevant technical developments in recent years. So we need to take a fresh look at these issues. And this difference can be examined from the viewpoint of the notion of intelligence and the notion of rationality. Rationality serves for many people as a measure of intelligence. So that notion is extremely important. It's a foundational notion. It's also important for many other fields, for example, economics, cognitive science, operations research, control engineering, and so on and so forth. In those fields, the notion of rationality is tied to optimality or optimization. In addition, this notion also brings up a whole can of worms and many other issues, for example, nature of human activity, human intention, intuition, instinct, and so on and so forth. So what I will do in this talk is first explore those notions, and then I will describe an example of cognitive architecture viewed as a kind of AI system. And then we apply those notions to examine the model and to see how it can shed light on those issues, the purported differences between AI and human intelligence. In that process, I will try to refine the notions of rationality, intelligence, human activity, intention, motivation, and so on. So first, the notion of rationality. The traditional notion of rationality centers on a hypothetical self-interested individual who seeks to maximize personal utility. Furthermore, it is assumed that the individual has complete information about all possible options and has a foresight of consequences from these options, and the capacity to solve a mathematical optimization problem to find the optimal solution through evaluating the consequences of all these options. And many mathematical properties were attributed to utility functions, for example, being transitive, being complete, and so on. Often linear functions are used. Now, that's a very stringent set of requirements. Herbert Simon proposed his bounded rationality, which relaxed some of these requirements. He recognizes that people often have to make less than fully optimal decisions because people are limited by, for example, the information they have, the capacity of their mind, the processing speed, the processing capacity in general, and the cost of gathering and processing information, and so on. Therefore, according to him, an individual may be a satisficer seeking to achieve a satisfactory but possibly suboptimal solutions. Now, the question is, what is satisfactory? So that's a big issue. Now, a bigger question in this regard is, what does being rational means for humans and human societies, historically and currently, beyond just economics or AI? There have been many different usage of this term. Sometimes they are vastly different. Beyond optimality or optimization, it often means some kind of logic in thinking. So in this case, the emphasis is on process of reaching a conclusion or a decision, not on the outcome. The outcome may not be optimal, but as long as you follow the logic, then it's rational. And instead of a standard logic, alternative forms of logics are also possible. Across cultures, there are many possibilities. And there are also other possible standards besides logic. For example, probability theory or statistics. Furthermore, historically, this term may also mean many other human tendencies. For example, following some moral, religious, or even aesthetic principles, or even some affective forces, as studied by sociologists and anthropologists from a long time ago and also recently. Furthermore, there are also three different versions of rationality in terms of three different mental domains, according to Gonzalez 2017. One is epistemic rationality, which deals with knowledge. And next one is a practical rationality, which is focused on human actions. And number three is evaluative rationality, which is oriented to choice according to values. These notions are important to the difference between AI and human intelligence. I will revisit those issues a little later. Now let's move on to intelligence. And well, if you look up a dictionary definition, it's very bland and uninformative, so completely useless. But Gonzalez 2017 identified two aspects of intelligence. I wouldn't call them definition. They are not really definition. One is intelligence is the faculty of working out how to achieve some goal. Number two is intelligence is something that can be measured and assessed, for example, through a psychometric approach, which are very well established. And in relation to the first aspect, there's often epistemological reduction. In other words, intelligence is often equated to computation, and computation is often equated to symbolic processing, as advocated by Newell and Simon. And in relation to the second aspect, there is a methodological reduction, a kind of a behaviorism for assessing intelligence, for example, using Turing tests to compare humans and machine, which is also very limiting. So we need to go beyond those. So another perspective brought up by Gonzalez 2017 is intelligence within the context of human activity, a philosophical notion. In other words, he wants to deal with human intelligence in a broader milieu. And this broader milieu is important to human intelligence, and therefore it's important to the difference between AI and human intelligence. Now I want to take a detour away from this notion for a brief period. I want to switch gear to talk about hybrid neurosymbolic models. I will show the connection of these two sets of topics a little later. We all know that neural networks and deep learnings are good at many things, and they achieved some spectacular successes in recent years. But people notice they have many shortcomings and limitations. And people notice that neural networks, including LLMs, transformers, and older neural network models, and the symbolic models have complementary strengths. So it seems to be a good idea to combine the two paradigms. Therefore, neurosymbolic models are being actively pursued. They may mitigate the weaknesses of each paradigm, so the result may be more capable, more versatile, more expressive models. But this is not a new idea. It harkens back immediately to the 1990s when the first batch of such models emerged. Even before that, in the 1980s, at the very beginning of so-called new connectionism, theoretical criticism of connectionist paradigm point to the need for integrating symbolic processing into neural networks, to say the least. For example, the work by Fodor and Perlician, and the work by Pinker and Prince, and also Gary Marcus at that time. But the actual computational models of hybrid neural network, hybrid neurosymbolic models emerged in the 90s, following those theoretical debates. So here are a few books from that era, for the sake of nostalgia. As far as I know, this book is the first book on this topic, Sun and Bookman, 1994. These books are collected volumes. In other words, they include a set of models, approaches, paradigms, methodologies, and so on. And there are many different ways of structuring neural and symbolic processes. So, but the problem is that many of them appear ad hoc or task specific or otherwise problematic. That includes not just those early models in the 1990s, but also more recent models. For example, this year there's this conference on neurosymbolic integration, and as far as I can tell, still the same kind of a problem persists. Now, the question is, how can we produce better models going forward? How should we best structure such models, given all these options and possibilities? How do we structure them in a principled and theoretically justified way? We would like to base such models on some fundamental theoretical principles. So I argued in the 1990s during the first wave, and I'm still arguing today to that community, a better approach for structuring such a model is structure them in a cognitively motivated and justified way. By that I mean a psychologically motivated and based way. And we look at the human cognitive architecture and build on that basis. And that's not something new. I mean, many people here are talking about the same thing. In particular, we need to take into account due processes, which are often known as the implicit versus explicit processes, or system 1 versus system 2, intuition versus reasoning, and so on. And this distinction has been popular ever since Kahneman's 2011 book, but it goes way back before Kahneman. Due process theory were discussed both by philosophers and psychologists. So I would argue that they constitute very solid theoretical and empirical foundations for neurosymbolic models. I'm not going to go into full-scale defense of due process theories, but I just want to show a few quotes. One is a quote from Kant. Thoughts without intuitions are empty. Intuitions without concepts are blind. We need both. That's due processes, which is already explained by Ricardo yesterday, not yesterday, the day before yesterday. And also another quote, logic is one thing and common sense another. Again, due processes. Logic remains barren unless fertilized by intuition. So in other words, you need to combine both. Now, in the philosophical literature, William James' distinction between empirical thinking and true reasoning has been cited a great deal. And also, Heidegger's distinction between the pre-ontological and the ontological is also similar to that. In the experimental science, in the experimental psychology, there have been a lot of empirical studies of implicit versus explicit learning, implicit versus explicit memory, unconscious versus conscious perception, and so on and so forth. This was also mentioned by Sean, I believe, the two stream of perception. And so there are many different due process theory. So here's my version as proposed in my 1994 book, in which I posited that cognitive processes are carried out in two distinct levels with qualitatively different mechanisms. Each level encodes a set of knowledge for its processing, and the coverage of the two sets overlaps substantially. In other words, these two levels may encode similar contents, but they encode these contents in different ways. One is symbolic, the other one is sub-symbolic, and so on. And therefore, different mechanisms are involved in processing them. And as a result, they have different degrees of accessibility. So one is more explicit, the other one is more implicit, and so on. And furthermore, these two different levels can potentially work together synergistically, complementing each other in various ways. So I refer to these 2 points as the two basic hypotheses. One is a dual representation hypothesis. It goes beyond the dual processes, but also hypothesizing the representational difference between the two. And the second one is a synergy hypothesis. And that's the reason why nature has chosen this particular design. And here's another more recent due process theory proposed by Kahneman in his 2011 book. According to him, there are two systems of processing. System one is typically fast, automatic, effortless, associative, implicit, and so on. System two is slow, serial, effortful, consciously monitored, and deliberately controlled. Here is another due process theory as proposed by Evans in 2003. According to him, system one is a rapid, parallel, and automatic. System two is slow and sequential, and so on. These two due process theories are highly similar. But furthermore, Evans also hypothesized about the relation between the two processes. According to him, system one is the default response. It's always there. And the system two may provide intervention sometime when intervention is necessary. So that's a default intervention relationship between the two systems. This is opposed to other possibilities. For example, parallel operation of system one and system two, or system two first and then bringing system one, or other possibilities. I'll get to those details a little later. However, notice that some of these characterizations may be simplistic. Therefore, it may be problematic. For example, as demonstrated in the literature, intuition can be very slow, not necessarily faster than the other process. Also, intuition can be subject to conscious control and manipulation. It's not completely automatic as characterized by these two. And explicit thinking can be engaged right from the outset and can be constantly present, not necessarily just the occasional intervention. So we need a more nuanced understanding. I mean, from their domain, their characterization may be accurate based on their empirical finding, but that's not generally true besides their narrow domain. And the Kahneman's domain is mostly decision-making, and the Evans' domain is reasoning. To have a more nuanced understanding, we need to ask many questions, especially with regard to the mechanisms underlying these two processes. For example, we can ask how deep is the processing, degree of precision, certainty of conclusion, and so on. How broad is the processing? How much information is involved? Or what is the quality of the information to begin with? Incomplete, inconsistent, and so on and so forth. And other questions. Furthermore, we need to separate two types of processes, procedural versus declarative. That's a distinction very well established in psychology. Procedural refers to action-oriented processes, and declarative is about factual knowledge and reasoning on that basis. And also, what is the relationship between explicit distinction and the procedural declarative distinction? And that's also an area of debate. And what is the mechanism behind these type of processes? So we need an overall theoretical framework for understanding these. And a cognitive architecture is the right kind of theoretical framework. And also because cognitive architecture is computationally implemented, therefore you can do a lot of things with it. To me, a computational cognitive architecture is a broadly scoped, domain-generic, computational psychological model capturing the essential structures, mechanisms, representations, and processes of the mind. In other words, the emphasis here is on psychologically realistic cognitive architecture for the sake of psychology. So that's a very narrow definition, and the people, for example, the soul people, would not agree with that definition, but that's fine. I mean, that's the kind of cognitive architecture I'm looking into, I'm working with. And specifically, I want to talk about the Clarion cognitive architecture, which is dual process and dual representational, involving both symbolic and neural representations. And that aspect is a key to Clarion. And it provides a general framework to facilitate more detailed exploration of the mind, what I call computational psychology. We specify computational detail, process details of psychological phenomena. And so we embody our theory of psychology in computer algorithms and programs. Therefore, simulation can be carried out. And the result of the simulation can be compared to the empirical data from psychology, neuroscience, whatever, for the sake of validation of the model or for further refining and enhancing the model. And this methodology of computational psychology is very well established. And its main product is enhanced understanding of the human mind. But its byproduct may be new ways of building AI system. So instead of getting into details of Clarion, which I really don't have time to do, let me highlight a few basic principles of Clarion. One is a division between procedural and declarative processes, as I mentioned earlier. The other one is a division between implicit and explicit processes. But within that, I also hypothesize two further distinctions. One is a division between implicit and explicit procedural processes. And the other one is a division between implicit and explicit declarative processes. In other words, there's a four-way division. Each of these types can be divided into two subtypes. And symbolic representations are used for explicit processes, and subsymbolic representations are used for implicit processes. So that provides a representational substrate for the implicit-explicit distinction, or in other words, it provides a kind of a magnetic explanation for the phenomenological distinction between the explicit and implicit. Well, explicit and implicit distinction is a empirically grounded, so it's more than just a phenomenological distinction. But anyway, so there are some other characteristics of human everyday activity that we need to take into consideration. One is reactivity, the other one sequentiality, routineness, and adaptation through trial and error. Clarion embody these. And also, the motivational basis of cognition and behavior must be taken into consideration. We need to explain why people or agents do what they do. In Clarion, we hypothesize the essential intrinsic motives known as the drive within Clarion. For example, affiliation, achievement, power, autonomy, fairness, and so on. These are well studied in psychology, in social psychology, industrial organizational psychology, educational psychology, ethology, and so on. And also, we need a metacognitive regulation on that basis. So these are the basic principles to implement these basic principles, here are some 4 major subsystems of carrion. Let me go over that very quickly. One is ACS, action-centered subsystem for dealing with procedural processes. The other one is NACS, non-action-centered subsystem for dealing with declarative processes. And motivational subsystem, MS, metacognitive subsystem, MCS. Each of these subsystems consists of 2 levels. The top level contains the explicit processes, and the bottom level contains implicit processes in all of these 4 subsystems. And these 2 levels operate in parallel. So it's not a default intervention. They operate in parallel. They interact. For example, if the explicit representation is activated, it will also activate corresponding implicit representation at the bottom level, and vice versa. So we refer to that as top-down versus bottom-up activation. And the learning can also occur through top-down and bottom-up flow. And coupled with reinforcement learning, it can perform autonomous learning throughout the system. I'm not going to get into the details here. So here are a few books about carrion, and this one is the most recent book on carrion, Anatomy of the Mind. It has a more up-to-date details. Even though that book was published in 2016, by now it's 9 years. We really need to publish a new book, as suggested by Ricardo already. And of course, I mean, we don't have to use backpropagation neural network. LLM can serve very well in the bottom level for implicit processing, but I'm not going to get into the detail. So let's get back to rationality and intelligence. Let's see how carrion can shed light on the discussion of rationality and intelligence in humans and in machines. In my view, traditional and bounded rationalities are all variations of the same old theme, with rationality as optimization. Bounded rationality, as proposed by Simon, did not go far enough, in fact. It did not take into full consideration the complexity and the subtlety of the human mind. So a question in this regard is, how rational are humans along this line of rationality as optimization? Of course, we have to take into consideration costs of being rational, being optimal, as pointed out by Simon already a long time ago. But we also need to take into consideration the roles of intuition and instinct, as pointed out by Dreyfus brothers, a role of affect, emotion, roles of aesthetic, moral, and other judgments, and also other aspects of the implicit mind, for example, habits, routines, customs and traditions, and religious and ideological beliefs. To some critics of AI, there lies the fundamental difference between AI and human intelligence. They claim that AI is optimization. They cannot deal with these. Therefore, AI is different from human intelligence, and AI can never be like human intelligence. Now, my question is, how can AI capture these characteristics of actual human rationality, not just an idealized version of human rationality? Well, here is I deal with an evolutionary argument. How much time do I have left? Five minutes. I thought I still have 50 minutes. But anyway, so I will have to skip that. Basically, it says that the evolutionary argument doesn't work, really. So according to Clarion, we need to take into consideration of human intuition and human instinct. And these are implicit processes, mostly at least. They have many irrational characteristics, but that's the reality of the human mind, the reality of human rationality. Furthermore, according to Clarion, we need to take into consideration human motivation and metacognition. And we need to take into account affect, emotion, and personality. And according to Clarion, these phenomena have a lot to do with essential intrinsic motives known as driving Clarion. I'm not going to get into the detail of computational models on that basis. I will refer you to the reference cited for each of these, for this one for moral judgment and so on and so forth. In other words, Clarion does not reduce complex mental processes to a simple, well-behaved utility function that can be optimized. It's much more complex than that, even though Clarion incorporates some kind of utility functions as a small part of it. And in terms of the domain of rationality, we talked about these three different rationality. As you can tell, epistemic rationality is captured by non-action-centered subsystem, and the practical rationality is captured by the action-centered subsystem, and evaluative rationality is captured by the combination of motivational and metacognitive subsystem. So we can analyze these notions within the context of these subsystems. Now the question is, how much time do we have? 0? 1-5. Oh, okay. Okay, so I can slow down now. All right. Okay. Yeah, that's because the previous talk was delayed. But anyway, so let's look into each of these. So one is practical rationality. A critique in this regard is, I quote, artificial intelligence follows a kind of instrumental rationality where the focus is on the means needed to achieve some given ends. But the rationality of means is not a genuine practical rationality. However, if you look at the Clarion, as I explained so far, we have those essential intrinsic motives or drives within the motivational subsystem, which determines one's ends or intentions, in other words, goals, and then the means for achieving those ends, which are the actions within the action-centered subsystem. So Clarion clearly does not rely on pre-given ends. It is free to choose its own goals based on many internal and external factors in a given context. But of course, those essential intrinsic motives are built into the model, but they correspond to evolutionary acquired motivational structures in humans. These are genetic pre-endowment. They are human universals, although with some individual variations. Now, next is evaluative rationality. Here's a critique of AI. It's kind of a rationality related to ends, priority, preference, values, but the ends of AI are chosen by designers and the software and the builders of hardware. Again, it's a kind of a predetermination. That's the issue. However, in Clarion, values arise from essential motives that I mentioned earlier, their activations and their possible satisfactions. From values, then the priority and the preferences are determined. And values in Clarion are assessed based on possibility and extent of satisfaction of these drives. along with their respective activated strengths. It's basically the weighted sum of the strengths of a drive and its possible satisfaction. And that's the value of, for example, an action or a goal or whatever. I refer you to this paper for details. Epistemic rationality, let me just skip that. Now let's move on to the notion of intelligence on the basis of our discussion of rationality so far. As discussed earlier, there are at least three aspects to intelligence. One is a goal-oriented behavior, two, measurability, and three, the context of human activity. In terms of measurability, Mikic and al. Showed that carrion can indeed perform well in psychometric intelligence tests to a level that is comparable to humans, not necessarily higher than humans, but not worse than humans either. It's kind of average, slightly higher than average human. And we used Raven's progressive matrices. That's a very well established intelligence test. In terms of goal-oriented behavior, I already explained Clarion is goal-oriented and it can learn to accomplish tasks as guided by goals or in the context of goals. And furthermore, it addresses how goals emerge from the intrinsic essential motives and so on. The third aspect, human activity, is a huge topic. The short answer here is Clarion can indeed capture major characteristics of human activity and intelligence in that context. So let's look into human activity. A key aspects of human activity, according to Gonzalez 2017, seem to be human intention, which is characterized this way. Intention requires a volition oriented towards chosen goal. It can include affections or sentiments. Intention also includes some kind of assessment, which requires acceptance or rejection of values, and so on. On that basis, Gonzalez 2017 distinguishes between true activities of humans versus mere behavior of AI. Let's look into that distinction here. Well, let me skip those other characteristics which I mentioned earlier, but it's now related to Gonzalez's discussion, so I just skip that. And in terms of the origin of intention, Gonzalez said intention has an internal origin in humans, which are intrinsically associated with a human being as a basis for free action. In contrast, AI has a starting point that's external to the performance self, because its purpose comes from the mind of the designer. The decision or the evaluation cannot be reduced to the means, because these requires taking into account aspects such as principles, rules, priorities. AI does not include genuine intention as a result. So its behavior cannot be described as a free activity. So here, what he's talking about is a kind of autonomy in relation to intention, goal, purpose, priority, and so on. I refer to these as autonomy of the motivation. It's related to what I mentioned earlier, the predetermination of ends. So what about carrion? So here is a notion from social psychology and also IO psychology, educational psychology, and so on. Intrinsic motivation. That is, engaging in an activity because of the inherent satisfaction of performing that activity rather than the expectation of extraneous rewards. There are a variety of experimental studies of intrinsic versus extrinsic motivations. The general finding is if people are intrinsically motivated, their performance improve. And educational psychologists made a big deal out of that, but I'm not going to get into that. So can this notion be captured in computational models? The answer in Clarion is yes, we can capture such a notion. Clarion, as I mentioned earlier, identify a set of essential intrinsic motives such as these. And then on that basis, it determines its goals and actions. So, so these actions are indeed, can indeed be intrinsically motivated. So there is indeed autonomy of motivation, intention, and agency in Clarion. Now, according to Gonzalez 2017, there are 3 other aspects of human activity. One is volition, and the other one is affect, and then value. So let's look into these. Affect, according to Clarion, arises from the interaction of these different subsystems. In particular, the action values within the action-centered subsystem and the activation or strengths of these motives or drives within the motivational subsystem. The combination of these 2 factors determine the valence of affect, and the emotion involves, of course, appraisal and so on and so forth. So I'm not going to get into the detail. So in other words, emotion and affect in Clarion are emergent based on the interaction of these subsystems instead of entity by itself. We don't have a module called emotion, but they are indeed present in Clarion without dealing with the issue of qualia. Now, volition. According to Clarion, it's a result of the sequence of processes going from motivational subsystem to metacognitive subsystem, then to action-centered subsystem. In other words, from drive activation to goal selection, then to action selection. That sequence, based on that causal direction of that sequence, we feel that we are doing something of our own free will, motivated by our own needs and desires. So we have a subjective sense of volition. So therefore, volition is also emergent in Clarion, but it's indeed present in Clarion without dealing with the issue of qualia again. Now, value. In Clarion, value arises from those essential intrinsic motives, as I mentioned earlier, which represents human genetic pre-endowment, evolutionary acquired human universals, but of course with individual or cultural variations. So the values are not universal, it could vary. But there are some universal invariants in this, but that's a separate issue. Anyway, in Clarion, we have the drive, then the goal arises on that basis, then actions are selected on the basis of goals, and so on. So the motivational subsystem, which contains those drives or motives, is the basis. From those drives, there emerges an axiology, a value system of its own. For example, let me just show one example. The values of actions are actually calculated within the action-centered subsystem based on cost minus based on benefit minus cost, where cost is determined by the amount of effort and the benefit is determined by the likelihood of achieving the goal from the effort and the degree to which to achieve the goal satisfy those activated drives and the strengths or activations of those drives. So value is intrinsic to Clarion. Therefore, it's premature to draw the conclusions that AI does not have a genuine activity, but a behavior with given ends as claimed by Gonzalez, even though it may be true of some AI, or human beings have self-determination, whereas AI has an auto-determination. However, I do agree with them two important points they made. One is the irreducibility of human activities to mere behavior, to actions satisfying a given goal. B is a need for evaluative rationality on top of instrumental rationality, those motives and the goals on that basis. Clarion clearly attempts to address both. So here's a concluding remark. I drew upon the philosophical analysis of intelligence, rationality, and AI model, and examined the specific line of work on cognitive architecture, which is due process, neurosymbolic, and motivationally oriented. Within the context of the model, I discussed the issue of different types of rationality, different conceptions of intelligence, essence of human activity, volition, intention, value, and so on. I argued that some recent computational models, AI models in a generalized sense, are more sophisticated than the philosophers often assumed, and they are capable of addressing many objections to the AI of the past. And Clarion provides a richer, more nuanced, more multifaceted account of human rationality and intelligence. In Clarion, rationality is not a single, static, fixed property, but dynamic, pluralistic, context-dependent, shaped by many factors, evolutionary, developmentally, and so on and so forth. And Clarion integrates due processes, intuition, instinct, learning, motivation, metacognition, emotion, personality, social interaction in addressing rationality and intelligence. It captures how rationality and intelligence emerge. It may be useful tools. Thank you very much.
Thank you so much, Professor Ronson. What a great work. That was amazing. So does anybody have a question? Okay, that was so quick.
Love the presentation. Thank you so much. Good as always. So many things I'd like to ask, but in service of the conference, I'll ask this. So a lot of your presentation was related to things that humans can do, things that AI can do, and obviously Clarion and consciousness, very important. So I'm kind of curious, do you believe that Clarion could be conscious in the same way that a human is conscious, or do you believe that there's a fundamental difference based on biology or whatever it might be?
Thank you. I deliberately avoided the notion of consciousness.
Sorry.
And, and that's a very difficult issue because consciousness usually, I mean, starting from Ned Brock, they distinguish two different kinds of consciousness, access consciousness and phenomenal consciousness. Who mentioned that? Ricardo, right? Yeah. And we can deal with access consciousness. That's no problem. Clarion deals with access consciousness very well, in fact. And the due process theory is a natural candidate for addressing that issue. But phenomenal consciousness, that's a much more difficult issue. I made some speculations, but they are mere speculations. I believe I published a paper in year 2000 or 2001, a sequence of paper, in fact, speculating on the nature of phenomenal consciousness and how Clarion may capture that. But that's those arguments are not very convincing to myself, so I'm not going to repeat them.
Thank you. And actually, I'll say that Stan Franklin's position was very similar. I think he felt that we did a good job of modeling access consciousness, but phenomenal consciousness was too mysterious, even though David Chalmers had said, why don't you just suggest that Lida was conscious and let somebody else go through the trouble of proving that it's not?
Yeah, David Chalmers has some weird ideas. I had extensive discussions with Stan Franklin on consciousness, and both in Memphis and outside Memphis. And as a result, we co-wrote the paper on consciousness. That was a very long time ago.
Yes. Thanks so much.
Hi. Ron, I was wondering that this duality that you proposed of implicit and explicit, and the symbolic and sub-symbolic, it seems to me that the problem is on the sub-symbolic, because we don't understand exactly how the sub-symbolic works. Actually, the proposal here is to associate sub-symbolic with neural networks. But in some sense, the sub-symbolic has to do with the interface to the world, okay? It's very good to process symbols, but the problem is how you reach the symbol, how you take things from the world and go to the symbolic point, okay? And then I would draw your attention to the notion of icon. That is quite interesting, because the neural networks can be a kind of iconic processing, but in my point of view, the notion of icon is bigger than the notion of merely, in other words, a neural network can be one possible way of having iconic processing, but there might be others kinds of iconic processing. So what do you think about this possibility of enhancing this idea of a sub-symbolic processing in terms of a more general iconic processing?
Yeah, I remember our discussion in the cars, a long car ride and a long discussion. So yeah, as if you remember, as I suggested that iconic representation and processes may be equated to embeddings in neural networks, or distributed representation in general. I mean, that's an older term, and that's probably a bit more generic in its connotation, not necessarily in denotation, but in connotation. And so actually, symbol grounding problem has been addressed in Clarion right from the beginning. I have some slides that mention that, but I skipped those slides because of a time constraint. So what we argued in those papers, starting from the late 1990s, I believe, in particular, one paper published, I believe, in year 2000 in the Journal of Philosophy and Psychology. The title is something like Symbol Grounding, a New Look and an Old Issue. At that time, it wasn't too old an issue. By now, it's really old issue. But anyway, so what we suggest is that we ground symbols as in the top level of Clarion, in the sub-symbolic activities in the bottom level of Clarion. And that bottom level can include perceptual processes, can include many other implicit processes. And through that, it can achieve some kind of sensory motor grounding, as argued by Hamed. And he's still clearly obsessed with that idea. Although, I mean, people are talking about other kind of grounding, referential grounding, for example, as argued by Moller and Millier. You cited that paper also, although our difference is you disliked it and I like it. But we really don't have time to get into argument on that point. But at least there's a sensory motor grounding. That's That's pretty straightforward.
Yeah, but I mean, when I talk about an icon, I talk a little bit more than just images. If you go to Peirce, for example, you'll see that Peirce talks about images, diagrams, and metaphors. So they are different levels of iconic processing that can be performed. And even though I believe that sensory grounding can work, for example, for images, they are not enough for describing our use of diagrams or our use of metaphors or metonym. So these are higher kinds of iconic processing that we are still to discover how to process them inside a cognitive architecture, at least in my point of view. And we need to find a place inside the cognitive architecture to put these kinds of capabilities.
I would disagree on the analogical reasoning. On those kind of sub-symbolic representations are actually pretty good at dealing with analogical reasoning. I have some papers dealing with that issue, and more recently, the paper I cited, the Mikic et al. Dealing with Raven's progressive matrices. That's an intelligence test, and that intelligence test is entirely based on analogy. Very interesting.
Thank you.
Professor Ron, thank you very much. It was an excellent presentation. I'm very grateful to attend it. And I would like to ask 3 questions, short answers or short questions. Now, the first one is that many so-called intelligent systems, their operation looks like that. Suppose that you have a ball and you leave it on a hill, not on the top. The ball will fall down to the lowest point. That means that it will minimize its energy. Many intelligent systems work like that. And somebody may suggest that this ball has an objective, has a means to achieve it, and so on. How does an intelligent system differ from a ball that rolls down a hill? That was the first question. Thank you.
Yeah, that's very interesting. Whether this intention and so on and so forth is in the eye of the beholder or actually in that system itself. And yeah, that's interesting distinction, the first person perspective versus the third person perspective. I mean, actually in the philosophical literature, there are a lot of debates based on that, first person versus the third person, with regard to consciousness and with regard to other notions. And so you just have to look into that. Why I believe that you are actually have intentions and consciousness, and not just a ball rolling down the hill. That's because I believe I have the intentions and consciousness, and you are similar to me, and therefore you do have that. And for machine, I mean, for AI system, we cannot use this strategy because they are so different from us. So we can look into their makeup. In other words, we have to get into the inside, get into their quote-unquote brain to understand that. And so if you go into Carrion, the inside of Carrion, then you see there is intention, there is motivation, and there is free choice.
Okay. Can I proceed to the next question? The second question has to do with representation. If we have an algorithm that we call it intelligent, for example, and it has some components, whatever, how do you represent these components? For example, if you do the implementation on a digital computer, at the bottom level, the bottom line is that everything is represented by strings of ones and zeros. But how do we interpret zeros and ones? Do we interpret them as numbers, as symbols, or what? So the question is, how do we represent the components of our intelligent system in a real world implementation?
I'm not sure I understand the question, but let me give it a shot anyway. A key point in Clarion is that there are two types of representation. You have representation for explicit processes, which is symbolic, and the representation for implicit processes, which is more distributed. So you cannot identify a particular neuron as representing a particular idea. In general, I mean, there can be exceptions. And these two types of representations are interconnected. So you have a distributed representation representing the notion of lunch. I'm a little hungry now. And once that distributed representation is activated, then the corresponding concept at the top level within the explicit processes are also activated based on the bottom-up activation flow, or vice versa. So these two types of activations work together to accomplish cognition.
Okay, thank you. And the last question is this. Suppose that humans disappear, or suppose that one of us goes to a planet where there are no humans. I guess that there will be no point of discussing about intelligence. So intelligence does not exist without humans. Now, humans cannot exist alone. We exist in teams, and we coordinate our actions in teams. We are effective because we act in teams. So probably intelligence is a capacity that gives us it fulfills our potential by our collaboration. So probably an intelligent system should be designed including other individuals collaboratively. Thank you.
Oh yeah, social processes are very important. I mean, to cognition, and also likewise, cognition is very important to social processes. Beyond the simple social processes, such as in an ant colony. I mean, in any case, so yeah, I will agree with the importance of social processes to cognition. But is that a requirement for cognition and intelligence? I don't know. I mean, maybe during the developmental process, social interaction is important. But that's an empirical question that has no answer, no clear-cut answer one way or the other. But on the other hand, I mean, everyone agrees that social processes are very important. Whether it's absolutely necessary or not, that's a separate question.
One more.
Well, thank you very much for your talk. It was really interesting, and well, there's a lot still to learn. Well, it's a very basic question. How far are we away from, getting there in terms of achieving, human intelligence in a broader sense, in a broader way? And so how far are we away? Are we actually getting there? Is this just the beginning of it? Or, this is just a bunch of ideas, something in practical terms, getting something to do things differently in a computational way. So it's a very basic, maybe philosophical question.
We're still very far. And those people were worried about AI takes over the world and kill all human beings. And I don't think you need to worry about that. I mean, we are still very, very far. That's my personal view. Many of my colleagues would disagree. But anyway, we are making progress towards that kind of AI. And it seemed to me some of the philosophers are behind. They still look at AI as from the previous generations of models, and the kind of models presented here shows that we are making progress towards a more human-like artificial intelligence. Actually, I mean, it's very heartening to see so many people here are discuss those issues: intention, emotion, personality, and so on and so forth. I've never been to a conference there are so many talks on these topics, those human-like features of intelligent systems. So there seems to be some kind of a convergence, at least within this community, and that's very good to see.
Okay, thank you.
Thank you so much, Dr. Sun, Georgios.
Okay, thank you so much. And well, let's take a 20 minutes break. So virtual attendees, we will back soon in a few minutes. Thank you.
Doctors, we take a photo. Outside.
Let's continue with today's session. The next presentation will be presented by Anastasia Navratskaya. Anastasia, are you ready? Anastasia, we can't hear you.
Anastasia? Anastasia, we can't hear you.
Anastasia, we can see your screen, but we still cannot hear you. Anastasia, please still talking. Maybe we have some issues. Professor Alexei, we cannot hear you too. Okay, wait a minute, please. We have some issues that we need to solve.
Recording in progress.
Okay, Anastasia, please, can you
Yes,
talk a little? Okay, we can hear you.
all right.
Thanks. You can start, please.
Now I will be proceeding with the presentation. So we have developed, I'll need to introduce myself. I'm Anastasia. I'm from National Research Nuclear University. This work is in our collaboration with my professor and Anatoly Dolgich, and Alexey Vladimirovich Samsonovich. So we have developed, among other things that we're developing in the lab, a platform for an in-depth study of social interactions between users and virtual agents. The platform is basically a visualization where you can plug any cognitive architecture or like another model, and it will visualize everything. It will voice everything, and there will be an interface with the virtual actors that I will show on other slides. This platform is intended for the study of models of social agents. It allows for testing agent-human interactions in real-life settings. It's compatible with agents of any nature. It enables remote multimodal social interactions. So, for example, we can read the expressions on one's face. We can maybe even in the future read the intentions, like using their voice and things like this. It can recognize tonalities of speech, and the agent can use recognized intentions to augment reasoning in communications with the user. Our platform integrates OpenAI and Unreal Engine 5. So we use Unreal Engine 5 for visualization and the OpenAI for communicating with the user in natural language. Here you can see a diagram of how our platform works. It's not very complicated. It has a speech-to-text server, text-to-speech server, and it connects with OpenAI and our internal cognitive architecture that we can plug into it. Among other things, we've used technologies like for other things, like as we've mentioned before, speech-to-text and text-to-speech, also for lip sync and for various other models. Specifically for the models of agents, we use MetaHuman because it is the most, I think in Unreal Engine it's the most closest to state-of-the-art, I think, visualization of a human, like a human-like actor. So our projects that are based on this technology, among everything else, include virtual tutor, the one we're focusing on heavily in the last year. Virtual psychodiagnosed, poster presenter, receptionist, virtual cocktail party, and roundtable. Roundtable is the one I will be demonstrating today. They are varied in how well they are developed, and yes, we focused mostly on virtual tutor and virtual roundtable. Others are mostly, I think, either scripted or just, not very advanced. Here is the user interface of our virtual tutor. You can enter the text of an essay, and then the virtual tutor will give you a criticism in places where it's necessary. The way that our platform is different from, for example, writing an essay using like normal ChatGPT or another LLM is that it never writes the essay for the student. It just provides appropriate criticism based on some criteria that we can plug in, and it has a system of transitioning between different states, that are scripted for the essay. So, like, for example, first we develop the outline, then we, for the essay, develop different arguments, then the conclusion. So it goes in steps that are defined by the cognitive architecture on the backend. So Here is an example of a person using the virtual tutor. The cognitive model specifically implements self-regulated learning via moral schemas of BICA, representing knowledge as vectors in a semantic space. I think there are 4 given vectors. OpenAI GPT-4o allows virtual tutor to maintain social engagement. So it basically serves as an interface where we basically tell the virtual tutor what to say, but then OpenAI is like an interface for communicating that in natural language, as like how a real human would say it. And in an experiment involving 48 undergraduates, our system produced a significant improvement in essay quality assessed on 16 different criteria. And now we will show you a virtual roundtable. It is an example of, well, our system, but the thing is that it uses 2 models. Will show that interactions between the 2 or more people are possible. So these people will serve one of them as an optimist and the other one as a critic, someone more pessimistic than the first one. So the idea is that they should balance each other out. Right now, I will change the screen I'm sharing. I will show you the demonstration in real time. So now I will explain the well, how to use it. Basically, first you will hear an introduction. So the actors will say what they are talking about, and then they will ask the audience, so they would ask you to maybe ask some more questions. And the way you'd ask those questions is like using your microphone. Just imagine that you're asking me the questions. Yes, and then hopefully the virtual agents will listen and they will respond accordingly. There might be a bit of a delay and there might be some bugs. I can't guarantee that this will go absolutely smoothly, but we'll try anyway. So right now I will share the screen of the application. Well, it might take a while for it to load, and then well, you can interact with them, well, just the same way you would interact with me, basically. So yes. Sure. So I hope you can see them, right? Okay.
Okay, Anastasia, so we can make a question to the agents?
Not yet, I guess. I have to apologize. There is a little technical problem because Anastasia forgot to switch the Zoom channel. so that the sound of the agent will be heard by you. And it just may take another half a minute, or Anastasia could show you a video recording of the session that we just created.
Okay, no problem, don't worry.
Anastasia, why don't you show the video from your PowerPoint? No. There is no sound. Закройте это, покажите видео. Just 1 second.
Alright, so I think we've been having some technical issues right now. So I will just show a video of the demonstration.
Please share your screen. Anastasia, please share your screen.
Of course. So in the demonstration, two people interact with the agents.
Okay, don't worry, go ahead.
What do you think about AGI and its future? What do you think about AGI and its future?
Advanced General Intelligence (IGI) could revolutionize many fields by performing complex tasks, but this also raises ethical and practical challenges. Exploring these implications can be a fascinating area of study and can offer valuable insights into technology's role in society.
IGI revolution. That's just CP chatter. Real world, we are drowning in challenges. Let's fix the mess I creates first, then talk about fantastical schemes.
While it's true that current technologies come with challenges, discussing IGI isn't just science fiction, it can help us anticipate future needs. Maybe asking others for their views could open up new perspectives and ideas.
Talking about IGI's future? Sure, but don't get lost in dreamland. Let's get real. Challenges we face now need attention. Anyone got thoughts on handling ISMS today?
Well, sure. I think that we can't really handle AGI since we can't really even handle normal artificial intelligence right now and the ethical questions that it poses. For example, I believe that AGI might pose a threat to the existence of humanity, and I do not believe that we are currently equipped to deal with that. What do you think about it? Do you agree or disagree?
Totally agree. IGI is a massive risk. Let's tackle today's issues first. Building understanding now can help manage the tech better without getting overwhelmed.
To me, the most important question is how do you achieve AGI? Like, what technology would you need to develop it? For example, is BICA really of any use for achieving AGI? or LLM would be sufficient? What do you think?
Achieving IGA will likely require advances in neural networks, computational power, and innovative algorithms. Techniques like LUM could play a role, but continued research and collaboration are key. Would you consider exploring more about these technologies to deepen your understanding?
Sure, exploring technologies can help, but let's not forget the ethical mess we're in now. It's not all about algorithms, you know. Got any ideas, folks, on tackling these headaches today?
Yes, this is exactly why I think that biologically inspired cognitive architectures have a great importance for the development of AGI. They not only allow us to build the necessary architecture and techniques, but they also help us to develop the right framework that will ensure the ethical quality, the safety and transparency of the future AGI.
It's great to see your curiosity and confidence in the potential of biologically inspired cognitive architectures for IGI. These approaches indeed offer promising pathways, and focusing on ethical and transparent frameworks will help guide us toward a responsible future.
While I'm skeptical about IGI coming anytime soon, I do respect the optimism. Let's keep it real though. Folks, how do we tackle ethical dilemmas in I today to prepare for tomorrow?
All right, so that's it. That's all I wanted to share today. Well, obviously there could be a demonstration, but well, I think it's enough to see the video of us interacting. The idea is that you can interact with the system through Zoom. So everything like speech to text and text to speech is produced locally on well, our system. And then so these are the really heavy operations that we need to take care of. And then well, the visualization is just well, translated straight to you. And that's it. So if you have any questions now, then I can
Anastasia, I think you still can try to show your demonstration, but first you need to switch the audio channels in
Yes, of
Zoom.
course. I have already switched the audio channels. It was it was the antivirus interfering that time.
But we hear you.
No, I mean not right now.
Are you speaking through a different computer? Okay. Why don't you try the demonstration then? I think we still have like few minutes. Am I correct?
Okay, can you hear me? Yes, if the attendees agree. Okay. Yeah.
Well,
we have a
meanwhile,
few
if
minutes.
somebody has question, thank you very much.
Don't worry,
And
go ahead.
meanwhile, if there are any questions that we can answer about this demonstration, which is going to happen in a minute, we could answer. So I guess Anastasia will guide you through the final part of her presentation.
What do you think about AGI and its future?
IGI holds immense potential to transform industries and daily life significantly. Exploring its implications is both exciting and essential as it could open new opportunities and challenges. How do you see it impacting our future in practical terms?
IGI sounds more about sci-fi dreams than reality. We've bigger worries right now. Why not focus on what actually helps today?
I understand your concerns about focusing on immediate challenges. However, exploring IGI can inspire innovative solutions for today's problems. Why not invite the audience to share their perspectives on what balance might be beneficial between immediate and futuristic tech pursuits?
Let's bring it down to earth. How can we balance chasing IGI fantasies and fixing real-world issues? What do you think, folks?
Okay. Can we continue to the conclusions of this?
No, you are supposed to ask question now. Talk to the agents. Can you do that? Just talk in the microphone.
Okay.
All right, folks, let's chat it. What do you think about balancing our current tech needs with dreaming big about IGI?
How can we acknowledge that something is in fact AGI, for example?
Exploring what aspects of technology could be considered as IGI is a fascinating journey. It offers an opportunity to deepen our understanding of I's capabilities and potential. Would you like to learn more about how IGI concepts might shape our field?
IGI is all hype without substance. Instead of chasing shadows, let's deal with the tangible tech that can make a difference now. How do IGI fantasies help us solve real issues today?
While IGI may seem distant, its pursuit sparks innovative ideas and discussions that can lead to practical advancements in current technologies, broadening our options for addressing real-world issues.
Chasing IGI may distract from solving today's issues. But alright, let's hear what you folks think. Does this futuristic journey really spark ideas that help now?
But regarding that, let's suppose we have AGI. How we would know that it is AGI in fact, and this could be used for different applications. But is there like an operational test that we can do to assume that something is AGI or not?
Honestly, defining real IGI is a headache. No magic test yet. We are fumbling around in the dark. Maybe focus that curiosity on making current I work better.
Okay. Thank you so much. Professor Alexei, can we finish this demonstration?
Yes, thank you. I believe it was really successful. Thank you very much. I hope you enjoyed it.
Thank you, Professor. That was an amazing work,
Thank you.
actually.
Thank you very much for your comment. Yeah, happy to hear that.
Okay. Well, I guess we can continue.
If there is no time for question, then just go ahead with the next presentation.
Thank you, Doctor.
Thank you.
Well,
okay, let's continue with the next presentation that will be performed by, in this case, okay, sorry about that. The presentation is supposed to be presented by the Dr. Naredo, but instead will be performed by Dr. Leiva.
Okay, let me give you some background about myself. I belong in Simba staff to a group that use research to produce intellectual property, to produce technology, and then transfer this technology to the industry. We were very successful with this kind of research. Our technology went in PC computers for IBM. Also, the laser printers of Hewlett-Packard uses our technology inside. AT&T also uses our technology in their telecommunication systems. And to give you an example, the first internet access point in the world were designed by us, and we were designed together with Bell Labs for AT&T and Lucent Technologies. So this is the idea. My idea to work in this area is also to understand life. I mean life, to understand what is the technology we are made of. Is impressive, that technology. We cannot achieve until now to something similar. And my purpose is to understand that technology and create the new interfaces between the machines and the humans or the life for the future. Okay. Everything starts with this book. It's a very inspired book for me. Edwin Schrödinger gave a set of talks in 1943 in the Trinity College at Ireland, and he tried to. What happened? It's going. And his idea. No, excuse me. And the idea of him was to explain life based on the laws of physics. At the end, all of us are made of atoms. So he tried to explain life based on thermodynamics and also from using quantum theory. In his book, he made this assumption: a living organism continually increases its entropy and thus tend to approach the dangerous state of maximum entropy, which is death. It can only keep alive by continually drawing from its environment negative entropy. And this negative entropy starts everything in my head. So I try to understand what was negative entropy. So this is the answer I wanted to answer. What prevents living beings from approaching the dangerous state of maximum entropy, which is death? I mean, all your atoms are in the environment everywhere, and we are okay, because negative entropy is not. Okay, let's try just to demonstrate that negative entropy is not the answer. Suppose we have a number of particles in a confined space, a certain temperature, volume, pressure, and then we let them to occupy a bigger space, And and then we can start to see all these particles due to kinetic energy to bounce each other and also to the walls. So we will have something like this. And once you have a space, a given space, the number of microstates, which are W, are big, but they are finite. Okay? So entropy is defined by this equation. And what we can see is that entropy is not other thing than a measure of the randomness of the system. If you have a bigger container, W will be bigger, bigger, bigger. More bigger than the stars in the universe. And then we can define from this formula the negative entropy. And if you consider that each of these microstates have the same probability to appear, then negative entropy is the probability each one of these microstates has to appear. So we can, from here, we can say that negative entropy is not the solution to maintain life. We can say it, if we translate those equations to life, what we can say is those equations are sufficient to maintain life. The first one means that if we have now a structure of atoms, this structure, if there is only one, so we maintain all our particles together and working. If this is one, that means that we have only one set of atoms and they work properly. Also means that this entropy is zero. And also probability disappears and there is only one configuration possible. Okay. The second argument to construct my answer is the cell. The cell was discovered in 1873. It's a very complex system. Is what we can say is the fundamental unit of life, is what we can say. And but to work, I prefer to use this model, very simple model. The cell is nothing else than an amazing molecular flexible manufacturing. Okay, so it uses raw materials, amino acids, ATP, ions, and produce products, messenger RNAs, proteins, and enzymes. Okay? In the operation of this factory produces heat and also produces waste. This heat and this waste is what can make the cell to stop functioning properly. If you don't remove heat, then the particles inside the cell start vibrating in a bigger frequency, start to augmenting the temperature, and you can break the bonds, the atomic bonds that maintain the union of the molecules, and then the system stops. Also, if you don't take the waste out, what you are doing is adding more particles to the system, and also these particles can stop the functioning of the cell. So we can say that heat and waste are the entropy, add the entropy of the system. Those things that are very, very amazing is these molecular robots that we call enzymes. Those micromolecular robots behaves like intelligent machines. And this is very amazing when you see working them in the cell. Okay. Then the next subject is the DNA that was not discovered, explained by Watson and Crick in 1953. And this is something amazing also. It's an amazing molecular data library. And this amazing molecular data library is about 3,000 million base pairs. And they use a very simple molecular atomic systems. Those are the bases. This structure is about 154 billion atoms. And with this, you can do everything. You can build the being and you can make it alive. It drives the life of in all the life of the being. You have here, for example, a fixed budget of atoms, and with this budget of atoms, you can construct this being in 20 days. So you need to have the blueprints of the being to be built, the information to create the machine and tools necessary to construct the being, the specialist builders to build and interconnect the entire infrastructure, the engineers, the project manager, and also you have the information to continue the physical transformation of this being in the different phases of their life. Also, we have the software, and also we have the firmware of the system. We have here in this structure the information about the operating system that will manage the in-place infrastructure of the life. We have here also the behavior of the being, whether it's a rose, a dolphin, a monkey, everything is here. Also, we have the information to processing for all the processing system to interpret information and making decisions, the communication protocol of the neural network, the processes to manage memory infrastructure, the feedback to control the system, to maintain life, and the intelligence to provide itself with food and shelter. Here we define intelligence in this way. We need to use consciousness to define intelligence. For us, is the set of processes based on information. It's executed and controlled by consciousness to achieve a goal. So we have here in this structure life, how to produce life and how to maintain life. Okay, so what we can say is that to produce and sustain life requires data and processes for everything, data and processes. And these data and those processes are in this memory, stored in this memory. And those data and processes is what we call information with meaning. And for having in this small structure all the information we need to produce and maintain life, it seems that, no, it must. Nature must follow an information system like the information system referred by Claude Shannon in his theory of information. And we need to have mechanism to data encoding and data compression. So information system used by nature, and this is an example of producing a protein. There is an enzyme called transcription factor that goes when the cell receive an order, goes and look for the chromosome that will be used to produce that protein. And when this gene is found, this transcription factor start and put a tag. This tag is later used by RNA polymerase to decode the complete sequence and produce a replica, which is the pre-messenger RNA. Once this little molecular machine produce this pre-mRNA, then there is another machine called pleistosome that read the complete pre-mRNA and start cut and say that it takes out all of the information that is not used for decoding a protein. Then when this mRNA is done, they leave the nucleus, and outside there is another machine called ribosome that this machine decodes and reads the code words of the three RNA bases at the time and produce the protein. So what we can say is that information really is what preserves life. It's not a negative entropy. So we can probably rephrase the Edwin Schrödinger statement saying that a living organism continually increases its entropy and thus tends to approach the dangerous state of maximum entropy, which is that it can only keep alive by continually drawing information from its main storage devices, which is DNA. And that gives us an idea that for us, for this group that I work with, which is very important, is one, we know for the electronics, we use a logic of only two symbols, 1 and 0. Nature uses a logic based on 4 symbols that are the bases used in the DNA. And also, there is another work we need to do is to try to understand or decipher the information system nature used to maintain life. I mean, to decipher the codification mechanism and also the compression system. And also to try to understand how a few million of atoms, which are the enzymes, have an intelligent behavior, and also where this intelligence resides, because there are very small structures of atoms, and they behave in an intelligent way. They never make mistakes. And that's it.
Thank you very much, Dr. Leiva, for an interesting presentation. So, does anyone have a question? Well, I guess, okay. Okay, sorry.
Hi. I have seen in the past other people trying to do similar kinds of things, like, for example, Robert Rosen in the 90s and Sung Ji with the Bopalator, how you connect your kind of research with these other studies that has appeared during time?
I was not aware of these works. What I can tell you is that doing this kind of research, we have now a patent that protects in some way the communication protocol of the nerve system, and it works. So we know a little how it works and how to connect to the nerve system, and it will be something very useful because in the future, if we can connect to the through a nerve, through an axon, to the central processing of vision, we probably make the people that is blind to see again, and those kind of things. Our mission is to produce technology from knowledge, so we are doing that.
Thank you.
Thank you for your presentation, Dr. Leiva. The question is, I like a lot this very last question you have there on your slide, like where intelligence resides. Do you have a hypothesis for that?
Not.
Any idea? Or
No.
I mean, because this is a very elementary building block that you're talking about, and somehow you claim that there is some sort of intelligence embedded in that block.
This is amazing, seeing this million of atoms working together to do a task, like the ribosome that produces proteins. I don't know, really. Yeah. I start talking with people in materials, physics, with them, try to exchange information and also ideas. Where can this information reside?
Maybe, I don't know, could be an idea of working from the perspective of complexity theory, because it might be that this sort of intelligence might be an emergent behavior within this building block.
It's more the answer is more toward the quantum theory.
Okay, so it's more in the physics and the. Okay, thank you. Very interesting.
Thank you so much, Dr. Leiva. Very interesting work. So, thank you.
Well, let's continue with the next and last presentation for the today's session. That will be performed by the Dr. Gustavo Palacios.
Hello. Okay, I believe you should be seeing the presentation.
Yes,
is that right?
Yes, we can. So go ahead, please.
Very well. So good afternoon, everyone. My name is Gustavo Palacios, and I will be talking with you about our paper titled Frames of Reference as a Means to Process and Codify Perceptual Inputs. These are some of the points we will be touching, and let's continue. I will try to be brief so you guys can go grab something to eat. So first, Sensation and perception are two fundamental cognitive functions that are essential for human beings and other animals to interact with their environment. Because of this, a lot of effort is devoted to bringing models of machine learning and artificial intelligence to make use of these functions. Most notably, or usually, they come in the form of vision or sometimes hearing systems. But despite of this importance, the computer systems lack the ability to correctly process the stimuli presented to them. So on this presentation, I'm going to be talking a lot of frames of reference or reference frames. So what are those? In psychology and neuroscience, they are a coordinate system against which the properties of an object are measured. And this will be important later on the presentation. So which properties? Well, the stimuli we process every day has certain characteristics or properties. Here on this presentation right now, you are seeing some of the auditory characteristics, but this is true for every other type of stimuli. So we have two kinds of characteristics or properties. Usually we divide them on physical, which are those ones that we can measure using certain instruments, and which are correlated to perceptual characteristics. The only difference is we cannot measure the perceptual characteristics because they live in our brains. This is how we assign or we give meaning to what's physical. So in computer systems, the processing of environmental stimuli has a really strong tendency to focus on specific high-level domains. And this makes it really difficult to characterize stimuli and correctly interpret that stimuli. So just to help us arrive at this problem, we studied the state of the art. Very quickly, we checked several cognitive architectures in order to see how they were processing perceptual information. So the first thing we can notice here is most of them use psychology or neuroscience to process the information or as inspiration. And most of them have at least one perceptual system. The most common one is vision, usually, but sometimes we can see auditory processing. The thing here is most of them focus on a very specific domain. In auditory, which it's really, on which you can notice it a lot more, you can see that most architectures focus on either a language or sometimes music, although not any of these ones reported here. So then we focused on how they are processing the information, how they represent the information, and if this information representation leads to the construction of different levels of abstraction. And we can see that most cognitive architectures do not take into account different levels of abstraction, even though that's how most of the cognitive sciences literature treats the information. So what we conclude from here, well, we know that stimuli features, although really important to how we process information, they provide a lot of information, and that information is often ignored, lost when the computer systems process on really specific domains. And also, in most cases, there is no way to represent information across different levels of abstraction, which is, in our opinion, important, quite important. So, okay, what support we can find in cognitive sciences about these levels of abstraction and about frames of reference? We used or we inspired ourselves on 3 specific disciplines of the cognitive sciences: psychology, linguistics, and neuroscience. Each one of those provides with different kinds of information and support. On psychology, we have the work of Moore, which states that the perceptual process is divided into different hierarchies, each one building upon the information obtained from the previous process. So we have 5 perceptual stages and 1 sensory one. And we build the information using this hierarchy. On linguistics, we have a lot of ways on which we, regardless of the language that we speak, how we talk about certain topics. So, for instance, color, regardless of the language you're speaking, there you can see a remarkable ability to assign labels to the colors and also compare colors between them in a way such that we can talk about which of these colors is closer to another one, right? So we can talk about which color would be the mixture of yellow and red, or which one of these is closer to a red than to a yellow. Aside from that, we have spatial relations. Regardless of language, we have certain systems that help us talk about things in different perspectives. I can talk about how I can see, things, and on this image, I can see this little Lego guy in front of the house, but I can also switch my reference to talk about how this Lego guy could be seeing things. And that occurs regardless of language. So that means that we can all do these kind of transformations. And lastly, in linguistics, we have the metaphors. The metaphors are a way of understanding and experiencing something by means of something else. So the example that Lakoff uses on his book, he uses several, but I think that this one helps get to the conclusion faster. Time is money. Time is a really abstract concept, and it's really difficult to explain. So what we did as a society was assign the properties of money to time. So in this way, we can spend time or save time, which would normally be something that could not be done, right? Because time is abstract. So that's on linguistics. And lastly, neuroscience, what support we find there? Well, again, this time using the auditory processing, because that's how this work first began. We can clearly see on all the ascending pathway from the ear up to the primary auditory cortex, a very notorious preference of neurons to certain frequencies. So we can see that neurons have what's called favorite frequency, which means that certain neurons will use one frequency as the basis onto which they will compare the rest of the frequencies. And if they perceive a certain sound, they will try to match how closely that sound's frequency is to my favorite frequency. And this also happens in the auditory cortex. We have 3 different areas, core, belt, and parabelt, all of which are tonotopically ordered, and we can see these preference in certain frequencies, which means that they are using a reference to compare everything they are provided. So that leads us to our proposal. The proposal here is the frame of reference, which would be a data structure that would allow us to encode stimuli from the environment and use that processing to generate percepts at different levels of abstraction. We propose on this paper specifically different attributes and functions, and I will try to go over them really fast. So I'm sorry if I just skipped some information. You can ask later if you're interested. So about the attributes, we propose 3 main attributes. Later, maybe some more can be added. So first, different levels of abstraction. This is really important because, well, we talked about Moore and her work. Here we are talking about how each stage of the perceptual process will build its percepts through its own set of frame of reference, which would be populated with the characterization or the information resulting on the percepts from the previous levels. So we can see here a little example on which I have a frame of reference, which is using time and distance to compare the stimuli. And if we get enough information on distance and time, we can use that to compute several points in another frame of reference, more abstract, that it's using time and velocity as the references. If we repeat this process once more, we would get acceleration instead of velocity. So this is the idea, just using our perceptual information, right? So this leads us to the second attribute. We have different time scales. Now, to allow us to compute one frame of reference and transform it into a higher level of abstraction frame of reference, we need several executions in the lower level. So by this logic, each execution of this acceleration frame of reference would require at least 2 executions of the velocity, which would mean that at least I need 4 points in the distance. This phenomena is known as temporal heterogeneity, and we can see it on Sandoval Arraiga's paper. And lastly, our last attribute would be the context dependency. So we are using references to measure the properties of our stimuli, and as such, using several definitions of context, we know that context shapes whatever it is we are measuring. So in this sense, these references work as the context of whatever it is I am processing, which means that context, or in this case the reference, will determine how a stimuli or percept is interpreted. Changing the context should also modify how we interpret that stimuli or that percept. And also, this would mean that every level of abstraction contains multiple contexts which we should be able to switch to interpret information in a different light. So that's it with the attributes of the frames of reference. Let's talk about the functions. We have 3 functions: distance, projection, and transformation. So we have the ability to compare between stimuli. That's what we call distance here. We use a Euclidean distance, but that doesn't mean that it's the only way. So to use this, we would only need to map our stimuli and compare the distance amongst them. So in this way, in this example, we can know that this point is closer to a purple than to a red. Projection is the ability to understand, use metaphors to understand stimuli. So the projection would allow us to take one point and create, let's say, a shadow onto another new reference to transform it to this new kind of way to process information. So this would allow us to compare things that normally would not be able to be compared. Lastly, the transformation is the process that answers the question, how can we produce more abstract and complex percepts using references, information from previous stages of reference frames. So on this way, how this works is when we populate a frame of reference, we use the information coded in this frame of reference to see how each point is related to every other. And by doing that, this function would help us characterize this information, allowing us to transform that into a single point in a higher level of abstraction, which would be in time populated with a lot of executions. So now, how did we prove this? What's our case study? We used, again, the information provided in Moore to select an experiment called a pitch discrimination task. This is a test that would allow us to measure the participant's ability to perceive change in the pitch of a sound and the direction of this pitch. The goal here was to use this test to compare human results with those of the architecture, but also to provide us with a metric to evaluate whether the architecture can or cannot process the pitch of a sound. So to do this, we took 58 young students between 18 and 25 years old. We provided them with a sequence of tones, and they had to answer whether the second tone had a higher, lower, or the same pitch as the first one. Then we applied the same test onto two versions of the architecture, one that had a higher level of tolerance to process frequencies, and another one that was more selective. We simulated 116 virtual agents, and we compared them to the human participants. Results, sadly, we were not able to really compare humans to the architecture on terms of how similar they were, because humans did not maintain a high level of similarity to other humans. So that only left us with if we could measure whether the architecture could or could not process a change in pitch on the sound. And now we can see here on our results that the architecture consistently shows positive results in the pitch discrimination tests. We can see that because our median is rather high and we have a low variance, right? Compared to humans, which had a tendency to both had a lot more mistakes, thus providing the proving that they were not able to discriminate the pitch changes, but also way more variance between them. And also we use the random variables just to see if we perform better than random variables, which we did. So the architecture shows better results in low variance, which allow us to conclude that although we cannot verify if the architecture behaves similarly to humans, because humans do not behave similarly to other humans, we were able to demonstrate that the architecture can discriminate and can detect these changes in pitch using frames of reference frames as the means to process this information. So what's next? What are we working on right now? We are working on expanding the frames of reference, this framework. So right now we're working on operations with nonlinear functions. I've shown linear vectors, but we are asking ourselves, what does a curve mean on these kind of references? How a context can be represented using curves instead of lines. We are trying to generate anticipation operations. That would be a new function with frames of reference, a function that would allow an architecture to predict what stimuli should be next based on my previous experience. And also we are trying to find a better experiment, an experiment that would allow us to distinguish whether an architecture can behave similarly to humans. Having said that, well, these are some of the references used on this presentation. Thank you very much for your attention. Sorry for the time. And if you have any questions, now it's the time.
Okay. That was amazing, Dr. Palacios. Well, does anyone have questions? No? Anybody? Yeah.
Great work. I appreciate it. I like how you structured everything. It was very well done. The one thing that seemed to occur to me is that the idea of abstraction in terms of just frames of reference seemed like it might be a little simplistic given the more general cases that might happen. So even like in the auditory, domain, if you were trying to characterize the differences between different musical genres, or just the abstract idea of what music is, or just these things that sort of go further and further away from the raw stimuli, it seems like there might be a little missing there in terms of those levels of abstraction, though I agree that they're very much needed. So I just wasn't sure if you felt like the notion of I guess this analogy that you had, like going from position to velocity to acceleration, where you were somehow differentiating almost across these other domains, is that sufficient, or you need something else that kind of, first off, weights certain dimensionality? One particular aspect is more important than others are less important, and is it really something you can specify in a coordinate kind of system like that in a priori way?
Okay, so I agree that certain concepts will be really, really far into the high level of abstraction. My hope here, because I can really, or haven't yet tested it, is that by using the hierarchy provided by Moore, we would be able to arrive there, because the later stages of perception actually deal with that kind of information. The only problem would be that we would need a lot of frames of reference from the lower levels, but also we would probably need to use reference frames from different perceptual systems. I mean, probably. So yes, it would be really, really complex, and I think it's one of the major issues with this proposal, because the complexity on the later stages is very high. So yes, I mean, I believe that it can be achieved, but it will require a lot of work.
Yeah, it'll be interesting to see. I'm definitely curious how far you can get with the bottom-up frame of reference approach, and I'm excited to see what comes of it.
Thank you.
Thank you, Doctor. Someone else? No? Okay. Thank you so much, Dr. Palacios.
Oh, thank you, guys. Have a nice day.
Well, everything that starts must end. And it is a little bit sad that this event has become to the end. I meet very brilliant minds, as I supposed to meet at the beginning. And today for me is sad. Okay, however, this is not the last BICA edition, so I hope to see you next year. Maybe here you are going to have some news in the next months. So please, I want your commitment to the next edition of BICA 2026. And I hope to see you with new ideas, new proposals, and also for me, for instance, this edition was very, very fruitful for collaborations. Okay, so at 1:36, I declare this 16 edition of BICA ended. So thank you very much for your participation, and I hope to see you in the next edition. And finally, a request is to have a final photo at the entrance of this building. Thank you very much for your cooperation.